Hello there, and welcome to Science for Sleep, where curiosity slows down for the evening and the universe speaks in whispers instead of alarms. Tonight, we're drifting into one of the strangest mysteries modern astronomy has ever encountered. Tiny flashes from deep space, signals so powerful they can briefly outshine entire galaxies, bursts of energy arriving from billions of light years away, lasting only milliseconds, and then disappearing again before anyone fully understands what caused them. Fast radio bursts, or FRBs, as astronomers eventually named them after realizing that saying unexplained ultra-powerful cosmic radio explosions from the far reaches of the observable universe every time was becoming a bit exhausting. Now, before we begin unraveling this mystery together, let me ask you something gentle and simple. Where are you listening from tonight? Is it late where you are? Quiet? Maybe the room is dark except for the soft glow of a screen. Maybe rain is tapping against a window somewhere nearby. Or perhaps you're listening while half asleep already, drifting between thoughts while the universe quietly hums overhead completely unnoticed. Funny, isn't it? For most of human history, the night sky looked silent, peaceful, predictable. Ancient people looked upward and saw stars moving slowly across the heavens like careful lanterns. They saw planets wandering, meteors flashing, comets arriving unexpectedly like cosmic guests who forgot to send a letter first. But mostly, space appeared calm, still, silent. And yet, the deeper we learned to listen, the stranger the universe became. Because the cosmos is not silent at all. It crackles, it pulses, it screams in frequencies our eyes can never see. If you find this little nighttime journey soothing, interesting, or simply a pleasant way to unwind after a long day, I'd be very grateful if you liked the video and subscribed. It helps this quiet corner of science and sleep continue drifting outward to others who might enjoy falling asleep, somewhere between black holes, distant galaxies, and very confused astronomers. Now then, settle in comfortably, loosen your thoughts a little, and let's begin with a mystery that arrived completely without warning. The first known fast radio burst lasted less than the blink of an eye, just a tiny flicker in the data, a sudden spike in radio waves recorded by a telescope in Australia, so brief that it could have easily been ignored. A computer glitch perhaps, a microwave somewhere nearby, a satellite, interference from Earth itself. Astronomy is filled with strange false alarms after all. Telescopes are delicate things. They pick up all kinds of noise. Signals bounce around from phones, aircraft, radar systems, storms, and occasionally from scientists accidentally causing problems themselves. There is a long and slightly embarrassing tradition in astronomy of discovering something impossible, only to later realize someone left equipment plugged in incorrectly. At one observatory, mysterious signals were eventually traced back to staff opening a microwave oven too early. Imagine discovering what appears to be an unknown cosmic phenomenon only to learn someone reheated soup at the wrong moment. Science can be humbling like that. But this signal was different, very different. Because when astronomers examined it carefully, they noticed something unusual hidden inside the burst. The radio waves had been stretched in a very particular way during their journey through space. Lower frequencies arrived slightly later than higher frequencies, almost as if the signal had travelled through enormous amounts of material before reaching Earth. That mattered. A lot. You see, space is not perfectly empty. Between galaxies there are tiny traces of gas, scattered particles drifting across unimaginable distances. When radio waves travel through this material, their frequencies spread apart slightly during the journey, almost like runners gradually separating during a very long race. And the amount of spreading told astronomers something astonishing. This signal had not come from nearby. It had travelled across billions of light years. For a moment, a tiny flash of radio energy from another galaxy had crossed the universe itself and reached Earth. Then it vanished. No warning, no repeat, no explanation. Imagine standing, alone in a quiet forest at night and hearing a single distant shout from somewhere beyond the trees. Loud enough to know it was real, brief enough that you cannot tell who made it or why. That was the beginning of the FRB mystery. At first, many scientists were skeptical, understandably so. Extraordinary claims require extraordinary evidence, as the old saying goes. A single unexplained signal buried inside old telescope data was not enough to convince everyone that the universe had suddenly developed a new category of bizarre behaviour. But then another burst appeared, and another, and another. Soon astronomers realised they were dealing with something entirely new. The universe, it seemed, had been firing off unbelievably powerful radio flashes all along. We just hadn't been listening carefully enough. Radio astronomy itself is already a fascinating idea when you stop to think about it. Human beings evolved under sunlight. Our eyes became tuned to visible light because that was useful for survival. We learned to spot movement in grass, recognise faces, and avoid walking directly off cliffs. Very practical things. But visible light is only a tiny slice of reality. The universe produces enormous ranges of electromagnetic radiation. Gamma rays, X-rays, infrared, microwaves, radio waves. Entire cosmic events unfold invisibly around us all the time. Radio telescopes allow astronomers to hear space in a sense rather than simply seeing it. And what they discovered was that space is noisy. Very noisy. Pulsars spin like giant cosmic lighthouses, emitting rhythmic radio pulses with astonishing precision. Quasars roar from the centres of distant galaxies where supermassive black holes feed on surrounding matter. Clouds of gas emit faint signals across interstellar space. Even Jupiter produces radio emissions strong enough to detect from Earth. The universe crackles constantly like an enormous electrical storm happening in slow motion. But FRBs stood apart from all of these known objects because they were too bright, too fast, too energetic. For a few milliseconds, a single fast radio burst can release as much energy as the sun produces over several days. Think about that for a moment. Our sun is unimaginably powerful. Every second, it converts roughly 600 million tons of hydrogen into helium through nuclear fusion. The energy produced lights the entire solar system. It warms Earth, drives weather, feeds ecosystems, powers oceans, forests, clouds, and every living thing you've ever known. And yet somewhere deep in space, unknown objects were casually producing similar amounts of energy in less time than it takes to snap your fingers. The scale of it barely feels real. One reason FRBs became such an obsession among astronomers is because they violated expectations so aggressively. Space usually behaves according to understandable patterns. Even violent things like supernovas or black holes follow rules that scientists gradually learn to recognize. FRBs arrived almost rudely. Tiny, sudden, extremely powerful, and often impossible to predict. It was as if the universe had started tapping humanity on the shoulder randomly at night and refusing to explain itself afterward. Naturally, scientists became deeply interested. Also, slightly sleep-deprived. That tends to happen when mysterious signals from distant galaxies begin appearing unpredictably at 3 a.m. The challenge was not simply detecting the bursts, it was locating them. Imagine hearing a camera flash somewhere inside a massive stadium while blindfolded. By the time you react, the flash is already gone. Finding the exact source becomes incredibly difficult. FRBs lasted such short periods that pinpointing their origins required astonishingly precise instruments. For years, astronomers could detect bursts, but struggled to identify where exactly they came from. Some theories suggested dying stars, others proposed neutron star collisions, some wondered about black holes. A few scientists cautiously discussed alien civilizations, although usually with the nervous tone of people aware they might accidentally become internet headlines. Because the moment astronomers mention extraterrestrials, everyone suddenly forgets the careful scientific reasoning and starts imagining little green men operating cosmic radio stations somewhere near Alpha Centauri. To be fair though, FRBs genuinely sounded strange enough to invite speculation. They appeared from deep space. They were incredibly energetic, and no one understood them. Human imagination tends to rush into gaps like that very quickly, but science works slowly, carefully, and over time, the mystery deepened even further. Because some FRBs repeated, this changed everything. Originally, many astronomers assumed fast radio bursts were catastrophic one-time events, perhaps stars exploding, neutron stars collapsing, giant cosmic collisions that destroyed whatever produced them. That made sense. After all, releasing such absurd amounts of energy sounded violent enough to destroy almost anything. But then one source fired again, and again, and again. Repeating FRB meant the object creating it survived the bursts. Suddenly entire categories of theories collapsed overnight. It was a little like discovering a supposedly extinct volcano casually erupting every Tuesday. Now scientists needed explanations for objects capable of producing enormous radio explosions repeatedly, without tearing themselves apart completely. This is where the story begins becoming wonderfully strange. Because the leading suspects behind FRBs are among the weirdest objects in existence. Magnetars, dense stellar corpses with magnetic fields so powerful they can distort atoms themselves. Objects capable of generating starquakes across their surfaces. Remnants of dead stars compressed so tightly that a teaspoon of their material would weigh billions of tons. And somehow, even magnetars may not explain everything. Some FRBs behave differently from others, some repeat constantly. Others remain silent forever after a single flash. Some bursts are smooth. Others contain complicated internal structures lasting fractions of milliseconds. A few appear inside ancient dead galaxies where young magnetars should not even exist, which means the mystery remains open. The universe is still sending signals, and humanity is still trying to understand them. There is something deeply fascinating about that idea. At this very moment, while you sit here listening quietly, somewhere unimaginably far away an FRB may already be racing toward Earth. A pulse of radio energy crossing galaxies in complete darkness. Passing stars, dust clouds, black holes, and empty stretches of intergalactic space for billions of years before eventually reaching our tiny planet. The burst itself may have happened before Earth even had complex life, before dinosaurs, before trees perhaps. And yet tonight, that signal might finally arrive at a radio telescope somewhere under the night sky. A brief whisper from deep time itself, then gone again. Astronomy often works like this. We do not observe the universe as it is now. We observe light arriving from the past. Every telescope is essentially a machine for looking backward through time. When astronomers study distant galaxies, they see ancient versions of them. When they observe stars, they see delayed images carried across space at the speed of light. FRBs take this feeling and intensify it dramatically. These signals crossed impossible distances simply to arrive as millisecond flashes hidden inside streams of radio data. And despite all our technology, despite satellites and supercomputers and observatories spread across entire continents, we still do not fully understand what we're hearing. There is something oddly comforting about that. The universe remains mysterious, not hostile necessarily, not magical, just bigger and stranger than human certainty. Every generation believes it has nearly figured everything out. Then the cosmos quietly introduces another puzzle, and reminds us we are still beginners staring upward from a small rocky planet. The night sky looked simple once, then telescopes revealed galaxies, then black holes, then pulsars, then dark matter, then FRBs. Who knows what waits next? Perhaps that is part of why astronomy feels so calming late at night. It gently rearranges our sense of scale. daily worries shrink a little when compared to signals travelling across billions of light years. Emails become less intimidating. Laundry piles lose some emotional power. Even awkward conversations from earlier in the day begin feeling less catastrophic when viewed against the backdrop of exploding neutron stars. The universe has a way of quietly placing things into perspective, and somewhere within that enormous cosmic machinery, fast radio bursts continue appearing without warning. Brief, powerful, mysterious, tiny flashes from the dark that astronomers still struggle to explain completely. Which raises an obvious question. If these bursts are truly among the most energetic signals ever detected in space, then what exactly are we looking at when a fast radio burst appears? For a long time, astronomers believed the universe was dramatic in fairly predictable ways. Stars exploded, galaxies collided, black holes swallowed matter while producing enormous jets of radiation. There were already plenty of strange things scattered across the cosmos, enough to keep scientists busy for centuries without needing entirely new mysteries, arriving unexpectedly in the middle of archived telescope data. And then one ordinary-looking signal changed everything, not with a giant explosion visible across the sky, not with some glowing object suddenly appearing where nothing had been before. No, the beginning of the FRB story was much quieter than that. It happened inside a computer, buried in old observations, hidden among noise, almost ignored completely. The year was 2007, although the signal itself had actually arrived years earlier, back in 2001. At the Parkes Observatory in Australia, astronomers had been using a massive radio telescope to study pulsars, those dense spinning remnants of dead stars that emit radio beams like rotating lighthouses. The Parkes telescope was already legendary by then, a giant white dish sitting beneath wide Australian skies, listening constantly to the universe in frequencies invisible to human eyes. Radio telescopes always look slightly peaceful from a distance, calm, motionless, quietly staring upward as if they're waiting patiently for the cosmos to speak first, and sometimes it does, although usually not in ways anyone expects. At the time, a young astronomer named Duncan Lorimer and his student David Narkovich were examining archived pulsar survey data. Nothing glamorous about it either. This was the scientific equivalent of digging through old storage boxes, hoping something interesting had been misplaced years earlier. Astronomy involves far more data analysis than most people imagine. Popular movies tend to show scientists gasping dramatically at glowing screens, while discoveries happen instantly. Real astronomy is often slower and much more repetitive. Hours of scanning graphs, sorting signals, filtering interference, arguing about calibration errors, drinking coffee that was probably better 6 hours ago. Sometimes entire careers pass without major discoveries, and then occasionally hidden inside mountains of ordinary information, something impossible appears. That is exactly what happened at Parkes. While reviewing the data, Narkovich found a burst unlike anything anyone had seen before. A sudden pulse of radio energy lasting less than 5 milliseconds, brief enough to disappear almost instantly, strong enough to stand out clearly against the surrounding noise. At first glance, it looks suspicious. Astronomers are naturally cautious people, because telescopes constantly detect false signals. Earth itself is noisy. Satellites interfere, airplanes interfere, electronics interfere, even kitchen appliances can interfere. One famous example became known as the Periton problem, where mysterious radio bursts detected at Parkes eventually turned out to be caused by staff members opening microwave ovens before the timer finished. Imagine publishing a groundbreaking cosmic discovery, only to learn someone reheated lasagna incorrectly. Science has these moments occasionally, so skepticism came naturally. But this signal behaved differently from ordinary interference. The burst showed something called dispersion. Now, dispersion may sound complicated, but the basic idea is surprisingly simple. Radio waves of different frequencies travel slightly differently through space filled with particles. Higher frequencies arrive first, lower frequencies arrive later. The longer the journey through cosmic material, the more stretched out the signal becomes. It is a little like runners separating during an extremely long marathon. And this burst was heavily dispersed. Far too heavily dispersed to have originated anywhere near Earth. That was the shocking part, because it meant the signal had travelled through enormous amounts of intergalactic space before reaching Australia. This tiny flash of radio energy had come from another galaxy entirely. Imagine hearing a single snap of a twig from billions of light years away. That was essentially what astronomers had just detected. The signal became known as the Lorimer Burst, named after Duncan Lorimer. And although nobody realised it immediately, astronomy had quietly entered a completely new era. At first, reactions were mixed. Some scientists were fascinated, others remained unconvinced. A single unexplained signal was not enough to establish an entirely new category of cosmic phenomenon. Extraordinary discoveries require repeated evidence. One burst could still be some unknown instrument malfunction or unusual terrestrial interference. Besides, the universe already contained enough mysteries without inventing new ones accidentally. Still, the signal refused to go away. The more carefully researchers examined it, the stranger it became. Its brightness implied enormous energy. Its duration was incredibly short. And its dispersion strongly suggested a source far beyond the Milky Way. If the calculations were correct, then whatever produced the burst released an astonishing amount of energy in only milliseconds. That created an immediate problem. In astronomy, energy output usually connects to size and duration. Big events tend to last longer. Supernovas can shine for weeks. Gamma-ray bursts may continue for seconds or minutes. Galaxies evolve over millions of years, but this thing released tremendous energy almost instantly, like a cosmic camera flash, and then nothing. Trying to explain that became difficult very quickly. Scientists proposed all kinds of possibilities: colliding neutron stars, exploding black holes, cosmic strings, magnetars. Alien civilizations inevitably appeared on the list as well, mostly because humans are apparently incapable of encountering unexplained signals without immediately imagining extraterrestrials trying to say hello. To be fair, history had prepared everyone for this reaction. Back in 1967, when Jocelyn Bell Burnell first discovered pulsars, the signals were so regular that astronomers jokingly labelled them LGM, short for little green men. The joke did not survive long once the true explanation emerged, but it demonstrated something important about science. Truly strange discoveries often sound impossible at first, because nature has no obligation to behave according to human expectations, and FRBs sounded extremely impossible, especially because nobody understood how anything could produce so much radio energy so quickly. For several years, the Lorimer burst existed in an uncomfortable scientific limbo, intriguing enough to study, uncertain enough to doubt. Then more bursts began appearing. That changed the conversation immediately. Additional radio telescopes started detecting similar events: brief flashes, extreme dispersion, enormous implied distances. The pattern was becoming undeniable. Fast radio bursts were real. The universe was producing them constantly. Humanity had simply failed to notice until now. That realization carried a strange emotional weight for many astronomers. Imagine discovering that the cosmos had been quietly flashing enormous signals overhead for billions of years, while humans remained completely unaware. Civilizations rose and fell. Empires appeared and disappeared. Entire species evolved. And all the while, distant galaxies were firing mysterious radio bursts across the universe unnoticed. There is something humbling about that. The FRB mystery also revealed just how dramatically astronomy had changed in modern times. Earlier generations relied mostly on visible light. They mapped stars and planets with telescopes designed for human eyes. but the modern universe is studied across the entire electromagnetic spectrum. Radio astronomy especially transformed humanity's understanding of space. Visible light tells only part of the story. Radio waves reveal hidden structures, invisible gas clouds, pulsars, black holes feeding inside galaxies, remnants of ancient stellar explosions, entire cosmic processes impossible to detect otherwise. And now apparently ultra-powerful millisecond bursts from deep space. The challenge with FRBs was not only detecting them, but understanding how common they truly were. At first, they seemed extremely rare, but scientists soon realized that rarity was partly an illusion created by limited observation time. Radio telescopes observe only tiny fractions of the sky simultaneously. Since FRBs last mere milliseconds, detecting one requires incredible timing and constant monitoring. It is somewhat like trying to photograph lightning strikes while looking through a drinking straw. The bursts may occur frequently everywhere, but you only catch them if you happen to be observing the right place at exactly the right moment. Once astronomers accounted for this, the numbers became startling. Researchers estimated that thousands of FRBs may occur across the observable universe every single day. Thousands. Most go undetected because nobody happens to be listening in the correct direction when they arrive. That means the universe is constantly erupting with these mysterious flashes all around us. The sky only seems quiet because human senses are so limited. There is something wonderfully eerie about imagining that. Tonight, while cities sleep and clouds drift overhead, distant galaxies may be firing radio bursts continuously across intergalactic darkness. Invisible storms crossing billions of light years. Tiny flashes racing silently between galaxies, and occasionally one reaches Earth. As the discoveries accumulated, astronomers began improving instruments specifically designed to catch FRBs in real time. This became one of the great challenges of modern radio astronomy, because early detections usually happened after the fact. Scientists would discover bursts only later while reviewing stored data. That was frustrating. Imagine hearing a mysterious noise outside your house, but only discovering it happened several days afterward. You cannot investigate properly because the event is already gone. Astronomers needed faster systems capable of reacting instantly. Observatories around the world joined the effort. Massive radio arrays scanned the heavens continuously. Computers analysed incoming data streams in real time, searching for characteristic FRB signatures. And the more scientists listened, the stranger the bursts became. Some FRBs appeared only once, others repeated. That distinction caused enormous excitement because it shattered earlier assumptions immediately. Originally, many researchers believed FRBs resulted from catastrophic events. Something exploding, perhaps. Neutron stars colliding, black holes consuming compact objects, massive stellar deaths releasing huge bursts of energy before disappearing forever. That idea worked reasonably well for non-repeating bursts, but repeating FRBs ruined the simplicity, because if a source repeated, it survived. Something out there was producing these immense radio flashes over and over again without destroying itself. That narrowed the possibilities dramatically. Suddenly, astronomers needed objects capable of surviving extraordinary energetic events repeatedly, and nature does contain such monsters. Neutron stars especially became prime suspects. These objects are among the densest things in existence. When massive stars die, their cores collapse so violently that protons and electrons merge into neutrons. The remaining object may contain more mass than the Sun compressed into a sphere only around 20 kilometers wide. Imagine crushing a mountain into the size of a sugar cube. Neutron stars are so dense that their gravity distorts nearby space dramatically. Their magnetic fields can become unimaginably powerful. Some rotate hundreds of times per second. Others release giant magnetic eruptions called starquakes. Among these stellar remnants exists an even stranger category, magnetars. And magnetars sound almost fictional when described aloud. Their magnetic fields are so powerful they could erase credit cards from halfway to the moon. They can distort atomic structures themselves. Nearby matter behaves strangely under their influence. If any known object could produce fast radio bursts, magnetars seem like excellent candidates, especially because magnetars are violent, unpredictable, explosive, exactly the sort of cosmic objects likely to frighten nearby planets immensely. Still, uncertainty remained, because FRBs refused to behave neatly. Some repeated often, others never repeated at all. Some emerged from young star-forming galaxies full of energetic activity. Others appeared in older galaxies where fewer young magnetars should exist. The mystery kept expanding instead of shrinking. And then something remarkable happened in 2020. For the first time, astronomers detected an FRB originating inside the Milky Way itself, not billions of light years away, not from another galaxy, from our own cosmic neighbourhood. The source was a known magnetar called SGR 1935 plus 2154. And suddenly, one major piece of the puzzle snapped into place. Magnetars truly could produce FRB-like bursts. That discovery was enormous because it connected theory with direct observation at last. Scientists finally had concrete evidence linking at least some FRBs to magnetar activity. But even then, the mystery refused to fully cooperate, because the Milky Way burst was weaker than many extragalactic FRBs, powerful by human standards certainly, but not quite matching the most extreme events observed across distant galaxies. Which suggested one of two things. Either magnetars sometimes produce vastly more powerful eruptions under special conditions, or multiple types of objects create FRBs. Astronomers still debate this today. That is one reason FRBs became such an important scientific obsession. They are not merely strange signals, they are clues. Clues about extreme physics, clues about matter under impossible conditions, clues about magnetic fields, neutron stars, intergalactic space, and perhaps entirely new astrophysical processes nobody fully understands yet. In a way, the discovery of FRBs reminded scientists of an important lesson repeated throughout astronomy again and again. The universe is under no obligation to make immediate sense. Human beings naturally crave explanations. We like clean categories and orderly systems. We want mysteries to resolve neatly after enough clever thinking. But space rarely behaves that way. Every time astronomers build better instruments, reality becomes more complicated. The night sky looked simple before telescopes. Then galaxies appeared. Then quasars, then pulsars, then black holes, then dark matter, and now FRBs. Each discovery expands human understanding while simultaneously revealing how incomplete that understanding still is. There is something strangely peaceful about that realization late at night. The cosmos remains alive with unanswered questions, not because science is failing, but because the universe itself is staggeringly large and endlessly detailed. Somewhere tonight, another fast radio burst may already be travelling toward Earth. Perhaps it began its journey before humans discovered agriculture, perhaps before mammals even existed. The burst itself may cross billions of years silently through expanding space before finally arriving at a radio telescope for less than a heartbeat. A millisecond from deep space, a whisper from another galaxy, and then, once again, astronomers will try to understand what exactly the universe is attempting to say. By now, astronomers had accepted something extraordinary. The universe was producing sudden flashes of radio energy, powerful enough to cross billions of light years, yet brief enough to vanish almost instantly. That alone sounded bizarre, but the deeper scientists looked into fast radio bursts, the stranger the situation became, because explaining what FRBs are turned out to be much harder than simply detecting them. At first glance, the name itself sounds almost disappointingly simple. Fast, radio, burst. Three very ordinary words stitched together into something that now occupies entire research programs around the world. But each part of the name matters. and each part hides something astonishing underneath. Let's begin with the radio part, because despite the dramatic headlines FRBs eventually generated, these bursts are invisible to human eyes. If one occurred nearby, you would not see some glowing beam tearing across the sky like science fiction lasers. Instead, the energy arrives as radio waves. Now, radio waves often sound harmless because humans associate them with ordinary things. Car radios, Wi-Fi routers, phones, music stations interrupting songs at exactly the wrong moment to tell you about local mattress sales. But radio waves are simply part of the electromagnetic spectrum, the same family as visible light, X-rays, and gamma rays. The only real difference is wavelength and energy. Your eyes evolved to detect visible light because sunlight dominates Earth's surface, but the universe itself produces radiation across a huge range of frequencies. Radio waves are especially useful for astronomy because they travel enormous distances through space without being blocked easily by dust or gas. That means radio telescopes can detect events occurring incredibly far away. And FRBs are among the brightest radio events ever observed. To understand how unusual this is, imagine standing somewhere completely dark and suddenly seeing a camera flash from another continent. Not a flashlight. Not a city, a single flash. That is roughly the scale astronomers are dealing with when observing fast radio bursts. Except instead of visible light, they detect radio energy. And instead of continents, the signal crosses galaxies. The fast part matters just as much. FRBs are absurdly short-lived. Most last only a few milliseconds. Some are even shorter. Think about how brief that really is. A human blink takes roughly 300 to 400 milliseconds. In the time your eyelid closes once, an FRB may already appear, release unimaginable energy, and disappear completely forever. That brevity creates enormous challenges for astronomers. Most cosmic events unfold over long periods. Stars evolve over millions of years. Supernovas brighten over days or weeks. Galaxies rotate slowly across cosmic timescales. FRBs are different. They happen almost instantly, like cosmic ambushes. If a telescope is not already observing the correct patch of sky at exactly the right moment, the burst simply vanishes unnoticed. This explains why humanity discovered them so late despite how powerful they are. The universe had probably been producing FRBs long before life existed on Earth, but humans lacked instruments fast enough and sensitive enough to catch them. It is a little like realizing thunderstorms have existed forever only after inventing microphones. And then there is the final word, burst. This one sounds straightforward too, but scientifically it carries enormous implications. A burst means a sudden release of energy, not a continuous signal. Not a repeating pulse like a pulsar ticking steadily through space. An FRB is more like an explosion, a quick discharge. Something releases huge amounts of radio energy in a tiny fraction of time, and then the signal is gone. The obvious question becomes, what could possibly create something like that? That is where the mystery truly begins. Because FRBs combine several qualities that should not naturally coexist. They are extremely powerful, extremely brief, and often extremely distant. Usually, large energy outputs require large systems operating over extended periods. The sun shines continuously because fusion occurs constantly across enormous volumes of plasma. Entire galaxies emit tremendous radiation because they contain billions of stars. But FRBs compress incredible energy into microscopic time windows. Some bursts release more energy in milliseconds than the sun emits over several days. Others may equal months of solar output. And they do this from objects likely no larger than cities. That is the truly unsettling part. The short duration tells astronomers something important about the source itself. Physics places limits on how quickly large objects can change brightness. If an object suddenly brightens and fades in milliseconds, The emitting region must also be relatively compact. Otherwise, light from different parts of the object would arrive at different times, stretching the signal out longer. In simpler terms, FRBs probably come from something small, astronomically speaking at least, which narrows the suspects dramatically. Normal stars become unlikely, entire galaxies become impossible. Instead, scientists focus on compact extreme objects, neutron stars, magnetars, black holes, perhaps even stranger things not fully understood yet. One reason neutron stars became such important candidates is because they already behave like cosmic laboratories for extreme physics. When massive stars die, gravity crushes their cores so violently that matter itself changes form. Electrons and protons merge into neutrons. The result is an object so dense that a single spoonful would weigh billions of tons. And yet neutron stars are tiny, only around 20 kilometers across. You could theoretically place one inside a major city, although doing so would ruin the city fairly quickly. These objects spin rapidly, possess intense magnetic fields, and store enormous energy. Some rotate hundreds of times every second. Others produce violent magnetic eruptions. Among neutron stars, magnetars stand out as especially terrifying. Their magnetic fields are the strongest known in the universe, and when scientists say strong, they mean truly ridiculous levels of strong. A refrigerator magnet is roughly 0.01 Tesla. An MRI machine may reach several Tesla. Earth's magnetic field is tiny by comparison. A magnetar? Around 1 quadrillion Tesla. Numbers like that stop feeling meaningful after a while. Under such conditions, atoms behave strangely. Space near the magnetar becomes physically distorted by magnetism itself. If one passed halfway between Earth and the Moon, it could potentially disrupt electronics worldwide. Fortunately, magnetars tend to stay very far away, because the universe occasionally demonstrates surprising kindness. These objects became leading FRB suspects, because they possess both the compact size and enormous energy needed. And in 2020, astronomers finally observed something remarkable. A known magnetar inside the Milky Way emitted a burst resembling an FRB. That discovery was huge. For the first time, humanity directly connected at least some FRBs to real astrophysical objects instead of purely theoretical models. Still, the story remained complicated, because FRBs do not all behave the same way. Some bursts repeat, others do not. This distinction matters enormously. Imagine hearing a loud explosion in the distance. If it happens once, you might assume something catastrophic occurred. But if the explosion repeats regularly, then clearly the source survives each event. Repeating FRBs forced astronomers to rethink earlier ideas immediately. Originally, many scientists proposed catastrophic explanations: neutron star collisions, black hole mergers, stellar explosions. Those models worked reasonably well for single bursts, but they failed for repeaters, because repeaters survive. One famous repeating source, FRB 121102, produced dozens of bursts from the same location. Over time, astronomers traced it to a small dwarf galaxy billions of light years away. That was another major breakthrough. Locating FRBs precisely allowed researchers to connect them with actual galaxies, rather than isolated flashes floating mysteriously through space. And the environments around FRBs turned out to be fascinating. Some originate in highly active star-forming regions filled with young, energetic stars. Others appear in older, quieter galaxies where fewer young magnetars should exist. This inconsistency created fresh confusion. Perhaps multiple types of objects produce FRBs. Perhaps magnetars behave differently under varying conditions. Or perhaps entirely new astrophysical mechanisms remain undiscovered. Scientists still debate these possibilities intensely today. There is also the question of why FRBs produce radio waves specifically. Space contains many energetic events, but not all generate strong radio emissions. Something about FRB sources creates highly organized coherent radio energy, meaning enormous numbers of particles emit waves together in synchronized ways. That requires unusual physical conditions. Imagine thousands of musicians striking the exact same note simultaneously with impossible precision. FRBs involve something similar on cosmic scales. Researchers suspect magnetic fields play a major role here. Violent magnetic rearrangements around neutron stars could accelerate particles intensely enough to generate coherent radio bursts. But the exact process remains uncertain, and FRBs continue surprising scientists. Some bursts show complicated internal structures when examined carefully. Instead of one smooth flash, they contain multiple subbursts drifting across frequencies in strange patterns. Others display polarization effects revealing information about magnetic fields encountered during their journey through space. In fact, FRBs have become valuable scientific tools precisely because they travel such enormous distances. Remember dispersion from earlier? The way lower radio frequencies arrive slightly later after passing through intergalactic matter. Astronomers realized they could use this effect to study otherwise invisible material spread between galaxies. Most ordinary matter in the universe is surprisingly difficult to detect directly. Stars and galaxies account for only part of what should exist, according to cosmological models. Much of the remaining normal matter likely drifts thinly across intergalactic space. FRBs act almost like cosmic flashlights passing through this material. By measuring how bursts become dispersed during their journey, scientists can estimate how much matter lies between galaxies. So these mysterious signals are not only puzzles themselves, they also help humanity map the invisible universe. That is one of the beautiful things about astronomy. Sometimes discoveries become useful before they become fully understood. FRBs may eventually reveal information about cosmic magnetic fields, intergalactic gas, dark matter environments, galaxy evolution, and the large-scale structure of the universe itself, all from signals lasting milliseconds. There is something wonderfully disproportionate about that. Tiny flashes carrying enormous scientific value. And yet despite all the progress, FRBs still preserve their mystery stubbornly. Astronomers now detect them regularly. Entire observatories specialize in hunting them. Artificial intelligence systems scan data continuously searching for new bursts. Some observatories can detect dozens in short periods. Still, major questions remain unanswered. What exact mechanism creates the bursts? Why do some repeat while others stay silent? Why are some vastly more energetic than others? Could entirely different categories of objects produce similar signals? And perhaps most importantly, what else might humanity be missing entirely? That last question lingers quietly behind all modern astronomy. Because FRBs were invisible to human knowledge until recently despite occurring constantly across the universe. What other phenomena remain hidden simply because our instruments are not advanced enough yet? The history of astronomy repeatedly teaches the same lesson. Every time humans develop better ways to observe the cosmos, reality becomes stranger. Telescopes revealed galaxies beyond the Milky Way. Radio astronomy revealed pulsars and quasars. X-ray observatories revealed violent black hole environments. Gravitational wave detectors revealed space-time itself vibrating from colliding black holes. And now, FRBs have revealed ultra-powerful millisecond radio explosions crossing billions of light-years. The universe keeps expanding conceptually faster than human certainty can keep up. Late at night, that thought feels oddly calming. Space is not finished surprising us. One of the reasons fast radio bursts became so famous so quickly is because the numbers involved sound almost unreasonable. Astronomy already deals with scales far beyond normal human intuition. Scientists casually discuss stars millions of times larger than Earth, black holes containing billions of solar masses, and distances so extreme that light itself needs billions of years to cross them. Even by those standards, FRBs stand out. because for a tiny fraction of a second, some of these bursts become among the most energetic events in the observable universe, and they do it almost instantly. That combination is what unsettled astronomers at first, not merely the total energy itself, but how concentrated the event appears to be. Imagine lighting a single match. Now imagine somehow releasing the energy of an entire power plant during the exact same tiny instant instead. That is the kind of absurd compression astronomers are dealing with when discussing fast radio bursts. To understand why FRBs seem so impossibly powerful, we first need to talk about energy in space generally, because the universe is constantly producing staggering amounts of it. Our sun alone generates around 380 septillion watts every second. That number is so large it stops feeling meaningful almost immediately. Human brains simply did not evolve for comfortable interaction with septillions. We evolved for practical concerns like, is that berry poisonous? And why is there a wolf looking at me? Cosmic scales arrived later. Still, the sun's output gives us a useful starting point. Every second, deep inside the sun's core, hydrogen atoms fuse into helium under enormous pressure and temperature. Tiny amounts of mass convert directly into energy according to Einstein's famous equation, E equals mc squared. That process powers sunlight, weather, oceans, ecosystems, forests, and nearly every form of life on Earth. The sun performs this continuously, steadily, hour after hour, year after year. FRBs, however, release enormous energy on radically shorter timescales. Some bursts emit as much radio energy in milliseconds as the sun produces over several days. Others may rival months of solar output, and all of it happens faster than a human blink. That matters because power depends not only on total energy, but also on how quickly that energy is released. Dropping a pebble gently onto a table and firing a bullet contain very different experiences despite sometimes involving similar energies. The timescale changes everything. FRBs compress immense energy into microscopic windows of time. That makes them phenomenally powerful. For a brief instant, some FRBs become brighter in radio wavelengths than entire galaxies filled with billions of stars. Pause there for a moment because that statement deserves proper appreciation. A galaxy contains enormous numbers of stars. The Milky Way alone may hold between 100 and 400 billion stars depending on which estimate you prefer and how optimistic the astronomer was feeling during calculations. Yet during an FRB, a single compact object can temporarily outshine all of that combined radio emission. It is like watching a firefly suddenly become brighter than an entire city skyline. Naturally, scientists wanted explanations immediately. The challenge is that energy does not appear from nowhere. Any object producing FRBs must somehow store enormous amounts of energy beforehand and then release part of it extremely rapidly. That immediately narrows the possibilities. Ordinary stars become unlikely because they are too large and relatively stable. Galaxies themselves evolve too slowly. Even supernovas, while vastly energetic, typically unfold over much longer periods. FRBs require something compact, dense, violent, something capable of releasing extraordinary energy almost instantly. This is one reason neutron stars and magnetars became such important suspects, because nature already provides them with absurd energy reserves. A neutron star forms when a massive star dies. During the collapse, gravity crushes matter so intensely that atoms themselves collapse. Electrons merge with protons, forming neutrons packed together at unimaginable densities. The result is essentially a giant atomic nucleus the size of a city. And these objects spin rapidly. Some rotate hundreds of times every second. That rotational energy alone is enormous. Now add magnetic fields. A typical refrigerator magnet produces a field humans barely notice, unless trying to rescue notes from falling off kitchen doors. Earth's magnetic field protects the planet gently from solar particles without causing daily inconvenience. Magnetars operate on entirely different levels. Their magnetic fields are so extreme they contain enormous stored energy. Twisting magnetic structures around the star can suddenly snap and rearrange violently, releasing tremendous bursts of radiation. Astronomers suspect FRBs may result from events like this: magnetic catastrophes on neutron stars, starquakes, sudden crust fractures, explosive rearrangements of magnetic fields stronger than anything humans can reproduce. The amount of energy involved becomes easier to understand if we compare it with familiar events. Take earthquakes. Earthquakes release energy stored gradually inside Earth's crust through tectonic stress. Most are relatively small, large ones can devastate cities, but even the most powerful earthquakes ever recorded would appear tiny compared to energy stored inside magnetars. A magnetar, starquake may release more energy in a fraction of a second than Earth's entire civilization uses over vast stretches of time, and somehow, some of that energy may become organized into coherent radio waves, detectable across billions of light years. That last part is important. FRBs are not merely energetic, they are detectable from enormous distances. That means the original burst must be unimaginably bright at the source, because by the time the signal reaches Earth, it has already spread outward across colossal volumes of space. Light and radio waves weaken with distance because they spread in all directions. Imagine shouting in a large empty field. Nearby, the sound feels loud. Far away, it becomes faint because the energy disperses over wider areas. FRBs face the same problem on cosmic scales. Yet astronomers still detect them clearly after journeys lasting billions of years. That implies astonishing original intensity. Some FRBs originate from galaxies billions of light years away. The signal may travel longer than Earth itself has existed before finally reaching a radio telescope on our planet. And after all that distance, after crossing intergalactic emptiness nearly beyond comprehension, the burst still stands out sharply against cosmic background noise. That is extraordinary. One reason scientists became fascinated by FRBs is because the bursts push physics toward extreme limits. They occur under conditions impossible to recreate fully in laboratories. Magnetic fields, gravity, density, and particle interactions all operate near the edges of known astrophysics. FRBs are essentially natural experiments performed by the universe itself. Dangerous experiments, spectacular experiments, but scientifically useful ones. Researchers analyze every detail carefully: burst duration, frequency structure, polarization, repetition patterns, dispersion through intergalactic matter. Each property reveals clues about the environment surrounding these objects. Some FRBs appear highly polarized, meaning their radio waves vibrate in organized directions. This usually indicates powerful magnetic fields near the source. Others display complex internal structures. Tiny subbursts drift across frequencies almost like notes, sliding during a strange cosmic song. A few bursts even repeat with curious patterns suggesting possible cycles or environmental influences. The deeper astronomers investigate, the less FRBs resemble simple explosions. Instead, they appear connected to dynamic environments filled with intense magnetic activity and extreme plasma physics. There is also another fascinating aspect to FRB energy: efficiency. The bursts emit strongly in radio wavelengths specifically, which requires coherent emission. Enormous numbers of charged particles must move together in synchronized ways. Ordinary thermal radiation does not behave like that. Imagine a crowd clapping randomly versus an orchestra performing perfectly in sync. Coherent radio emission resembles the orchestra. Nature somehow organizes particles under extreme conditions to produce coordinated radio flashes visible across the universe. Exactly how remains uncertain. Several competing models exist. Some involve magnetic reconnection events around magnetars, similar in principle to solar flares but vastly more energetic. Others suggest shock waves travelling through surrounding plasma. A few theories involve interactions between neutron stars and nearby material. There are even proposals involving black holes, exotic compact objects, or entirely new astrophysical processes not yet fully understood. And because FRBs vary so much, multiple mechanisms may exist simultaneously. That possibility excites astronomers because nature rarely limits itself to single neat explanations. The universe tends toward messy diversity instead. Different environments may create different classes of FRBs. Some repeat frequently. Others erupt once and vanish forever. Some appear inside young, energetic galaxies rich with star formation. Others emerge from quieter, older galaxies where fewer young magnetars should exist. The mystery keeps widening. And yet, despite all the complexity, the emotional reaction many scientists describe upon seeing an FRB remains surprisingly simple. Astonishment. Because the bursts compress so much energy into such tiny moments that they almost feel unreal initially. Human intuition struggles with scales like these. Imagine if all sunlight reaching Earth suddenly arrived compressed into milliseconds. Oceans would boil instantly, atmosphere would ignite, the planet itself would suffer catastrophic damage. FRBs perform comparable energetic feats routinely somewhere across the cosmos. Fortunately very far away. Distance is one of the universe's greatest safety features. Without it, astronomy would become considerably more stressful. This also raises an interesting point about visibility. If FRBs emitted their energy primarily as visible light instead of radio waves, some might briefly rival the brightness of entire galaxies across the sky. Fortunately for our eyes and civilization generally, most of the energy arrives in radio frequencies invisible to humans. Still, radio telescopes hear them clearly, and modern observatories have become remarkably good at listening. Facilities like CHIME in Canada revolutionized FRB detection dramatically. Unlike traditional radio telescopes focusing narrowly on small sky regions, CHIME scans enormous portions of the heavens continuously. The instrument itself looks unusual too, less like a classic giant dish and more like long metallic troughs stretching across the landscape. Not especially cinematic perhaps, but extremely effective. And once CHIME began operating fully, FRB discoveries exploded. Suddenly astronomers detected bursts constantly. New repeaters, complex structures, unexpected patterns, thousands of events. The universe, it turned out, was producing FRBs far more frequently than previously suspected. That realization changed the emotional texture of the mystery slightly. Initially, FRBs seemed rare and isolated. Now they appeared almost routine, cosmically speaking. The sky constantly flashes with these bursts. Humanity simply lacked instruments capable of noticing before. There is something wonderfully humbling about that. Reality often contains enormous hidden phenomena operating invisibly around us. Humans perceive only narrow slices of existence naturally. Visible light, audible sound, everyday scales. Science extends those senses artificially, and every extension reveals stranger layers underneath. Radio astronomy especially transformed humanity's understanding of the cosmos, because the radio universe behaves differently from the visible one. Quiet, dark regions suddenly glow. Invisible structures emerge. Objects undetectable by optical telescopes become spectacularly obvious. FRBs belong to this hidden universe. Tiny radio flashes crossing impossible distances, powerful enough to outshine galaxies briefly, brief enough to vanish almost before detection systems react. And still not fully explained. Perhaps that combination is what makes them feel so compelling late at night. They remind us that the universe remains active in ways human senses alone could never detect. Right now, while cities sleep beneath ordinary-looking skies, somewhere another FRB may already be erupting. A compact object releases enormous stored energy. Radio waves burst outward across expanding space. The signal begins a journey through galaxies, magnetic fields, drifting plasma, and intergalactic darkness. For billions of years it travels silently. Then eventually, perhaps tonight, perhaps centuries from now, perhaps long after current civilizations disappear entirely, that tiny flash reaches another world, a millisecond of energy, a brief disturbance in cosmic radio noise, and inside that fleeting signal lies evidence that nature can still produce phenomena far stranger and more powerful than human imagination first expects. Long before humanity understood fast radio bursts, before anyone imagined mysterious millisecond flashes crossing billions of light years, astronomers faced a very different problem. The universe looked too quiet, at least through ordinary telescopes. For centuries, humans studied space entirely through visible light. Ancient astronomers mapped stars with their eyes alone. Later, telescopes revealed planets, nebulae, galaxies, and moons in astonishing detail. The night sky slowly transformed from scattered points of light into a vast structured cosmos. Still, visible light tells only part of the story. A very small part, actually. The electromagnetic spectrum is enormous. Visible light occupies only a tiny narrow band inside it. A thin strip human eyes happen to evolve around because sunlight peaks there, and evolution tends to prefer practical solutions over cosmic completeness. The universe itself, however, is not concerned with human convenience. It produces radiation everywhere across the spectrum. Gamma rays, X-rays, infrared, microwaves, radio waves. Entire astrophysical events unfold invisibly overhead constantly, while human eyes remain completely unaware. Radio astronomy began almost accidentally in the 1930s, when an engineer named Karl Jansky started investigating mysterious static interfering with transatlantic radio communications. At first, he suspected thunderstorms or human technology. Instead, he discovered radio signals arriving from the center of the Milky Way. Without meaning to, humanity had accidentally overheard the galaxy itself. That discovery quietly changed astronomy forever, because once scientists realized the universe emitted radio waves naturally, entirely new ways of observing space became possible. Radio telescopes do not see the universe the way optical telescopes do. They listen. Not sound, technically, because sound cannot travel through space itself. Instead, radio telescopes detect electromagnetic waves at radio frequencies and convert them into usable data. Still, emotionally, the experience resembles listening more than looking. The radio universe feels alive with hidden activity. Pulsars tick rhythmically across space. Gas clouds hum faintly. Quasars roar from galactic centers. Black holes feed noisily on surrounding matter. And somewhere far beyond ordinary galaxies, FRBs flash suddenly through the darkness like cosmic lightning. The challenge is that these signals are extraordinarily faint by the time they reach Earth. Even the most powerful FRBs arrive weaker than many ordinary sources of local interference. That means radio telescopes must become incredibly sensitive, and building extremely sensitive instruments creates immediate problems, because Earth itself is noisy. Very noisy. Human civilization fills the planet with radio signals constantly. Phones, satellites, aircraft radar, televisions, Wi-Fi networks, military systems, communication towers, microwaves, even car electronics contribute to the chaos. Modern Earth practically glows in radio frequencies. Trying to detect faint cosmic signals through all that interference is a little like attempting to hear a whisper from another continent while standing beside a highway during a fireworks show. Astronomers solve this problem partly through location. Many major radio observatories are built in remote regions, far from cities and human infrastructure. Places where radio interference remains minimal. The Parkes Observatory in Australia sits beneath enormous open skies, far from dense urban noise. The Very Large Array stretches across the New Mexico desert. FAST, the 500-meter aperture spherical telescope in China, rests within a natural depression surrounded by mountains helping shield outside interference. and in Canada, CHIME quietly scans the sky, continuously searching for transient bursts. These observatories almost feel monastic sometimes, silent landscapes dedicated entirely to listening carefully. Because radio astronomy requires patience and extraordinary sensitivity, the instruments themselves are fascinating. Traditional optical telescopes collect visible light using mirrors or lenses. Radio telescopes instead gather radio waves using large metal surfaces and receivers. Since radio wavelengths are much longer than visible light, radio telescopes usually need to become enormous to achieve useful resolution. That is why many look gigantic. Huge dishes turning slowly beneath the stars, or massive arrays spread across deserts, or strange metallic structures stretching across valleys. Some radio telescopes even combine signals from multiple distant antennas using a technique called interferometry. By linking telescopes together electronically, astronomers effectively create a virtual telescope as large as the separation between them. This dramatically improves resolution. The Event Horizon Telescope used this principle to capture humanity's first image of a black hole by coordinating observatories across Earth itself, which is slightly wonderful when you think about it. An entire planet cooperating to observe something invisible. FRBs especially pushed radio astronomy into new territory because detecting them requires more than simple sensitivity. It requires speed, extreme speed. Remember, fast radio bursts last milliseconds. That means telescopes cannot merely observe slowly and carefully. Their systems must monitor huge streams of incoming data continuously in real time, searching for tiny transient flashes hidden inside enormous background noise. And the amount of information involved is staggering. Modern radio observatories produce enormous data volumes constantly. Some facilities generate terabytes every second. Computers analyze these streams automatically because no human could manually inspect everything fast enough. Artificial intelligence and machine learning now play major roles in FRB searches for exactly this reason. Computers sift through mountains of radio data searching for patterns matching burst signatures, brief flashes, specific dispersion properties, characteristic frequency drifts. Without advanced computing, many FRBs would remain buried unnoticed forever. In a sense, modern astronomy increasingly involves teaching machines how to notice strange things for us. That idea feels oddly fitting for FRBs specifically, because the signals themselves are so brief that humans would almost certainly miss them unaided. One particularly important concept in radio astronomy is signal-to-noise ratio. Every telescope receives noise constantly: thermal noise from electronics, atmospheric interference, cosmic background radiation, human technology. The challenge becomes identifying meaningful signals inside all that randomness. FRBs stand out because despite their brief duration, they're extraordinarily bright relative to surrounding radio noise. But brightness alone is not enough. Astronomers must also distinguish genuine cosmic bursts from local interference, and Earth loves making this difficult. At Parkes Observatory, mysterious bursts called peritons puzzled scientists for years because they resembled FRBs superficially. Brief radio flashes appeared unexpectedly across the telescope's data. For a while, nobody understood them. Then researchers discovered the cause: microwave ovens. Specifically, people opening microwave doors before cooking cycles finished. The escaping radio leakage produced signals oddly similar to FRBs under certain conditions. Imagine dedicating years to investigating mysterious cosmic phenomena, only to discover someone was impatient about reheating lunch. Astronomy can be deeply humbling sometimes. This incident reinforced how careful scientists must remain. Extraordinary discoveries require extraordinary verification, precisely because false signals happen constantly. FRBs survived scrutiny because they displayed characteristics impossible for local interference to mimic convincingly. Most importantly, dispersion. When radio waves travel across intergalactic space, Lower frequencies slow slightly relative to higher frequencies because they interact differently with scattered particles along the journey. This creates a distinctive stretching pattern. The farther the signal travels, the more dispersed it becomes, and FRBs displayed enormous dispersion values, far too large for local terrestrial origins. That is how astronomers knew these bursts came from deep space itself. In some ways, dispersion acts like a cosmic fingerprint. It not only confirms distance, but also reveals information about material lying between galaxies. This transformed FRBs from mere mysteries into scientific tools. By measuring how bursts become dispersed, researchers can estimate how much ionized matter exists across intergalactic space. And this matters because much of the universe's ordinary matter remains surprisingly difficult to detect directly. Stars and galaxies account for only part of the expected visible matter, predicted by cosmological models. The rest likely drifts thinly between galaxies in diffuse gas structures nearly invisible otherwise. FRBs illuminate this hidden material, like headlights briefly revealing fog during nighttime driving. Each burst carries information about everything it passed through during its journey. That includes magnetic fields too. Some FRBs display strong polarization effects. Radio waves become twisted while crossing magnetized environments, allowing astronomers to estimate magnetic conditions near the source and along the path to Earth. This means FRBs are not merely objects of study themselves. They are probes, tiny cosmic test signals crossing the universe naturally. The better humanity becomes at detecting them, the more we learn about space itself, and radio telescopes are the ears making this possible. CHIME became especially important in this story because its design differs dramatically from classic dish telescopes. Instead of rotating giant bowls, CHIME uses long stationary metal cylinders. As Earth rotates naturally, different sky regions drift overhead continuously. This allows constant monitoring of huge sky areas, perfect for catching unpredictable transient events. And once CHIME began full operations, FRB detections exploded. Hundreds, then thousands, repeating bursts, complex bursts, bursts from distant galaxies. The universe suddenly appeared full of FRBs. Humanity had simply lacked appropriate instruments before. This happens repeatedly throughout scientific history. Reality often remains hidden not because phenomena are rare, but because observation methods remain incomplete. Before X-ray telescopes, the high-energy universe stayed largely invisible. Before gravitational wave detectors, space-time collisions remained unheard. Before radio astronomy, pulsars and quasars were unknown entirely. And before advanced radio surveys, FRBs passed silently through Earth unnoticed. That realization carries a strangely peaceful feeling sometimes. The universe always contains more than humans currently perceive. There are likely phenomena operating around us right now that future civilizations will consider obvious once better instruments exist. Perhaps entirely new forms of astrophysical activity remain hidden inside data humanity still does not know how to interpret. Science continually expands perception outward. Radio telescopes embody that beautifully because they reveal a version of reality human senses could never detect naturally. If your eyes suddenly became radio sensitive tonight, the sky would look profoundly different. Invisible jets from black holes would blaze across space. Galactic gas clouds would glow softly. Pulsars would flicker rhythmically. Communication satellites would streak overhead noisily. And every so often, somewhere among distant galaxies, a tiny flash would appear briefly brighter than entire stellar systems combined. An FRB, a whisper from deep time-crossing billions of light-years. There is also something emotionally unique about radio astronomy compared to optical astronomy. Visible light images often feel immediate and beautiful. Galaxies swirl elegantly. Nebulae glow with colour. Stars scatter across black skies in recognizable ways. Radio data feels stranger, more abstract, more hidden. Astronomers often convert radio signals into visual representations artificially, because human brains process images more intuitively than raw frequencies. But underneath those colourful processed images lies something extraordinary. Humanity has learned to detect invisible vibrations from across the cosmos, using giant metallic structures listening carefully beneath Earth's skies. It feels almost improbable when described plainly. A species evolving on one small planet eventually becomes capable of detecting millisecond radio flashes from billions of light years away. That achievement alone is remarkable regardless of what FRBs ultimately turn out to be, and yet radio telescopes continue improving. New arrays grow larger, computers become faster, detection algorithms become smarter. Future observatories like the Square Kilometre Array may revolutionize FRB science completely by detecting vastly more bursts with unprecedented precision. Astronomers hope eventually to answer major questions. What exactly produces FRBs? Why do some repeat? How many types exist? Can bursts reveal hidden cosmic structures? Might entirely unknown physics operate near their sources? Each new telescope increases the chances of surprising answers. Because the universe rarely rewards observation with simplicity. Usually the better humans learn to listen, the stranger reality becomes. The first fast radio burst ever discovered was almost thrown away. Not dramatically. Not with scientists shouting at each other in some tense observatory control room while alarms flashed and coffee spilled across keyboards. Quite the opposite, actually. The signal sat quietly inside archived data for years, unnoticed while the world carried on normally. People went to work, cities expanded, entire television series began and ended, and meanwhile, hidden inside an old radio survey from Australia, one of the strangest discoveries in modern astronomy waited patiently for someone to recognize it. There is something fitting about that somehow. The universe rarely announces its biggest mysteries with perfect timing. Sometimes it simply leaves clues lying around quietly until humans become clever enough, or lucky enough, to notice them. The story begins at the Parkes Observatory in New South Wales, Australia. By the early 2000s, Parkes was already one of the most respected radio observatories in the world. Its giant white dish had spent decades listening to the cosmos, contributing to everything from pulsar discoveries to communications with NASA space missions. People sometimes call it the dish, which sounds charmingly simple for a machine capable of detecting signals from across the galaxy. Parkes had personality too. Radio observatories often do. Optical telescopes feel elegant and almost artistic. Radio telescopes feel patient, like giant metallic ears quietly leaning into the universe waiting for it to say something interesting. Most nights, of course, the universe behaves fairly predictably. Pulsars pulse, quasars radiate. Background noise hums softly through the receivers, and occasionally some nearby human technology causes chaos for everyone involved. That last problem turns out to matter a great deal in the FRB story. In 2001, Parkes was conducting a pulsar survey using a multi-beam receiver system. Astronomers were searching for pulsars by recording huge amounts of radio data continuously. The process generated enormous archives requiring years of analysis afterward. At the time, nobody was hunting fast radio bursts because nobody knew such things existed. That detail is important. Human beings often fail to notice discoveries simply because they are not looking for them yet. If you handed medieval astronomers a modern radio telescope, they would have no conceptual framework for interpreting the data. Entire categories of reality become visible only after science develops the language and tools needed to recognize them. In 2007, several years after the original observations, Duncan Lorimer and his student David Narkovich were examining archived Parkes data searching for pulsars. Again, not especially glamorous work. Astronomy contains large amounts of careful data inspection. Long hours studying graphs and signals hoping something meaningful appears. Most of the time, nothing revolutionary happens. and then occasionally the universe slips something impossible into the data almost casually. Narkovich noticed an unusual burst. Very unusual. A sudden flash of radio energy lasting less than 5 milliseconds. Strong, bright, and strange in exactly the right ways. At first, it could easily have been dismissed as interference. Radio observatories constantly detect false signals. Satellites pass overhead. Aircraft create noise. Electrical systems misbehave. Nearby electronics leak radio frequencies into sensitive equipment. Radio astronomers become deeply suspicious people for good reason. One scientist once joked that half of radio astronomy involves proving signals are not caused by microwaves, which, as it turned out, was more accurate than anyone realized at the time. Still, this burst behaved differently from ordinary interference. Its frequencies were dispersed. Higher radio frequencies arrived slightly before lower ones, creating a characteristic sweep pattern through the data. That effect occurs naturally when radio waves travel through enormous amounts of ionized gas in space. The signal looked exactly like something that had crossed intergalactic distances. And that created a serious problem, because if the burst truly originated outside the Milky Way, then its energy output became almost absurd. Astronomers checked calculations repeatedly. The numbers refused to become reasonable. That happens sometimes in science. Researchers encounter results so extreme they assume mistakes must exist somewhere. Instruments malfunction. Software errors occur. Equations get misapplied. Usually reality becomes less strange after careful verification. The Lorimer burst stubbornly remained strange. Its dispersion implied an origin far beyond our galaxy. Its brightness implied immense energy. Its duration implied a compact source, and nobody knew what could produce such a thing. The burst itself received the official designation FRB 010724, though most people simply call it the Lorimer burst now. At the time, however, nobody knew it represented the first known member of an entirely new astrophysical phenomenon. Initially, reactions across astronomy were cautious. Very cautious. One burst alone proves very little. Extraordinary claims require replication, especially in radio astronomy, where false signals occur constantly. Some scientists suspected terrestrial interference despite the dispersion signature. Others wondered about unknown atmospheric phenomena or instrument artifacts. A few researchers found the signal fascinating immediately. Others remained openly skeptical. That skepticism was healthy. Science progresses best when discoveries survive intense scrutiny rather than immediate enthusiasm. And honestly, the Lorimer burst sounded almost too dramatic to be real. A millisecond radio flash from another galaxy, powerful enough to rival enormous cosmic objects. That bordered dangerously close to science fiction. Complicating matters further, astronomers could not immediately find additional bursts. Years passed without clear confirmation. And during those years, the first FRB lived in an awkward scientific state somewhere between exciting possibility and questionable anomaly. Some researchers quietly doubted the entire thing. Perhaps the signal was merely an unusual one-time error. Perhaps the telescope malfunctioned. Perhaps Earth itself had produced the burst somehow. Then the situation became even stranger. Parkes Observatory began detecting mysterious radio flashes called peritons. Peritons resembled FRBs superficially. They appeared as short radio bursts with suspiciously similar characteristics. For a while, they caused enormous confusion because astronomers worried the Lorimer burst might simply belong to the same category of terrestrial interference. The mystery grew almost embarrassing. Researchers spent years debating whether FRBs were genuine cosmic phenomena or elaborate observational mistakes. And then came one of the most wonderfully human moments in modern astronomy. Scientists discovered that peritons were caused by microwave ovens. Specifically, staff members opening microwave doors before cooking cycles completed. the microwave leakage created brief radio signals detectable by the observatory. Imagine dedicating years of scientific investigation to mysterious cosmic events, only to discover someone reheating leftovers incorrectly. Somewhere out there, the universe contains black holes, exploding stars and magnetars capable of bending atoms with magnetic fields. Meanwhile, humans were accidentally confusing astronomy using soup. The discovery became legendary partly because it perfectly captured the strange balance between cosmic grandeur and ordinary human clumsiness that often appears in science. Importantly though, the Lorimer burst itself did not match the Periton signals fully. Its properties remained distinct. The case for FRBs survived. Then finally, additional bursts appeared. Other observatories began detecting similar events independently. Different telescopes, different sky locations, same bizarre characteristics, brief duration, extreme dispersion, enormous implied distances. At that point, skepticism started collapsing rapidly. Fast radio bursts were real. The universe genuinely produced mysterious millisecond radio explosions, and suddenly astronomy faced a brand new mystery no one had expected. That transition changed the emotional atmosphere surrounding the field almost overnight. What began as a questionable anomaly became one of the hottest topics in astrophysics. Researchers rushed to explain FRBs theoretically. Observatories developed new search systems. Entire collaborations formed around detecting more bursts. And through it all, the original Lorimer burst remained oddly iconic, not only because it was first, but because it demonstrated how easily enormous discoveries can hide inside existing data unnoticed. There is something profound about that idea. The signal arrived at Earth in 2001, but humans did not recognize its importance until years later. The burst itself may have travelled billions of years across intergalactic space before reaching Australia for less than 5 milliseconds. Then it sat quietly inside archived computer files while humanity remained completely unaware of what it represented. A cosmic message arriving long before anyone knew how to read it. Astronomy contains many discoveries like this. Pulsars were initially mistaken for possible alien signals. Cosmic microwave background radiation was first treated as annoying noise inside communication equipment. Even Neptune was discovered partly through mathematical irregularities, before anyone physically observed it. The universe often reveals itself indirectly first. FRBs fit beautifully into that tradition. The Lorimer burst also taught astronomers something humbling about observational bias. The universe may contain enormous phenomena humans simply fail to notice because existing instruments, methods, or expectations are incomplete. FRBs had likely occurred constantly throughout cosmic history. Millions, perhaps. Billions. Humanity remained unaware until radio telescopes and computing systems became advanced enough to recognize them. What else might still remain hidden? That question quietly haunts astronomy. Every major technological leap reveals new layers of reality previously invisible. Optical telescopes expanded the known universe enormously. Radio astronomy revealed pulsars and quasars. X-ray observatories exposed violent high-energy processes. Gravitational wave detectors uncovered colliding black holes through ripples in space-time itself. And now, FRBs. Each advance reminds humanity that our perception of reality is deeply limited by available tools. The cosmos itself remains far larger and stranger than human intuition naturally expects. There is another interesting detail about the Lorimer burst story too. The burst was so bright that if similar events occurred nearby inside the Milky Way, they would appear astonishingly strong to radio instruments. And eventually, decades later, astronomers finally observed exactly that. In 2020, a known magnetar inside our own galaxy produced an FRB-like signal. For the first time, scientists directly connected at least some fast radio bursts with magnetars, those ultra-dense neutron stars possessing the strongest magnetic fields known. That discovery retroactively strengthened the original Lorimer burst interpretation dramatically. The mystery had evolved from FRBs real into how exactly do these objects work, which is scientific progress in its purest form. One mystery solved only to reveal deeper ones underneath. Even today, the Lorimer burst remains slightly eerie when viewed historically. A single, unexplained flash buried in old data quietly introduced humanity to a completely new category of cosmic event, and the burst itself was tiny. 5 milliseconds. That is what feels almost absurd emotionally. An event lasting shorter than a blink transformed modern astrophysics. Entire observatories now specialize in FRB searches. Thousands of bursts have been detected since then. Machine learning systems scan skies, continuously hunting new signals. Researchers use FRBs to study intergalactic matter, magnetic fields, and extreme astrophysical environments, all because one strange signal refused to behave normally inside archive telescope data. There is something wonderfully understated about that beginning. No dramatic announcement from space, no giant visible explosion overhead, just a brief flicker inside radio noise noticed by careful scientists willing to investigate something unusual instead of dismissing it immediately. That willingness matters enormously in science, because nature rarely explains itself fully on first encounter. Sometimes discoveries begin as tiny inconsistencies, small anomalies, signals that look slightly wrong. At first, astronomers believed fast radio bursts were probably one-time catastrophes. That assumption made sense. The bursts were unbelievably energetic. Some released enormous amounts of power in milliseconds. Naturally, many scientists imagined violent cosmic events destroying whatever produced them. Colliding neutron stars, exploding compact objects, black holes consuming something unfortunate nearby. The logic seemed straightforward. If a burst emitted that much energy, surely the source could not survive repeatedly. And then one of them came back. That changed everything. Because the moment astronomers detected a repeating FRB, entire categories of explanations collapsed almost instantly. A repeating source meant the object survived the burst. Somewhere in the universe, something was producing gigantic radio flashes over and over again without tearing itself apart completely. That realization transformed FRBs from mysterious explosions into something far stranger. The story centered around a source eventually named FRB 121102. The designation sounds cold and technical, but that is typical astronomy behavior. Scientists discover one of the most mysterious objects in the observable universe and immediately assign it something resembling a Wi-Fi password. FRB 121102 was first detected in 2012 by the Arecibo Observatory in Puerto Rico, one of the largest radio telescopes ever built. Unlike earlier detections from Parkes, which still carried lingering uncertainty at times, the Arecibo burst mattered enormously because it confirmed FRBs were not unique to one instrument. Different observatories were hearing the same kind of signals. That alone strengthened the case for FRBs dramatically. But the truly astonishing part arrived later. In 2015, astronomers detected additional bursts coming from the exact same location, then more and more again. The source repeated. The reaction across astrophysics was immediate. Confusion first, then excitement, then more confusion. Because repeaters complicated everything. If FRBs repeated, then at least some of them could not result from catastrophic destruction events. Whatever produced the bursts remained active afterward. Imagine if lightning struck repeatedly from the exact same point in a cloudless sky. That was roughly the emotional effect repeating FRBs had on astronomers. The universe had just become significantly stranger. The repeating source itself behaved unpredictably too. Sometimes bursts appeared clustered closely together. Other times the object remained silent for long periods. There was no simple schedule initially, no obvious rhythm. just sudden radio flashes emerging from deep space irregularly like cosmic hiccups. Astronomers around the world turned radio telescopes toward the source obsessively. Every new burst represented valuable information. And because repeaters could be observed multiple times, scientists finally had opportunities impossible with one-time FRBs. They could localize the source more precisely. That became crucial. Using networks of radio telescopes working together through interferometry, astronomers eventually pinpointed FRB 121102 to a small dwarf galaxy around 3 billion light-years away. 3 billion! Pause there briefly because that distance matters emotionally as much as scientifically. The bursts began their journey toward Earth long before complex life fully flourished here. Long before humans existed. Long before mammals dominated the planet. Civilizations had not merely risen and fallen during that travel time, entire species came and went. And after crossing unimaginable distances, those signals reached Earth as tiny millisecond flashes, detectable only by giant radio instruments listening carefully beneath the sky. There is something deeply strange about that. But localization revealed another surprise too. The repeating FRB appeared associated with a persistent radio source nearby. Something in the region continuously emitted radio energy even between bursts. This hinted that FRBs might originate from highly energetic environments, perhaps supernova remnants, perhaps active magnetars, perhaps something even more exotic. The mystery deepened. And then astronomers noticed something else. The bursts themselves contained structure, very complicated structure. Originally, people imagined FRBs as simple flashes, one quick pulse, clean and straightforward. Reality disagreed. When scientists examined repeating bursts closely with better instruments and higher time resolution, they discovered astonishing complexity hidden inside milliseconds. Some bursts contained multiple sub-pulses, others drifted across frequencies. A few showed bizarre internal patterns almost resembling organized structures. It was like zooming into a lightning strike and discovering miniature storms hidden inside it. One especially fascinating behavior became known as downward frequency drifting. In some repeating FRBs, higher frequencies appeared first while lower frequencies arrived slightly later within the burst itself, not merely because of intergalactic dispersion this time, but due to processes happening near the source. The effect resembled descending musical notes. Naturally, astronomers became obsessed, because patterns imply physics, and physics means clues. Scientists began comparing FRB structures with known astrophysical phenomena. Pulsars, magnetars, plasma interactions, solar flares, shock waves. Nothing matched perfectly. The burst looked partially familiar yet fundamentally alien at the same time. Repeating FRBs also varied enormously in brightness. Some bursts appeared relatively weak, others became extraordinarily powerful. Sometimes the same source produced wildly different energies over short periods. That inconsistency complicated theoretical models further. Nature refused to behave neatly. Then astronomers discovered additional repeating FRBs, and things became even stranger. Some repeaters followed possible cycles. FRB 180916 displayed a 16-day activity pattern. The source produced bursts during certain periods and remained mostly quiet during others. Another repeater seemed connected to much longer cycles. Suddenly, researchers wondered whether orbital motion played roles somehow. Perhaps FRB sources existed inside binary systems, orbiting companion stars or black holes. Maybe surrounding plasma environments periodically blocked signals. Maybe magnetars rotated through active magnetic phases. Or perhaps entirely different mechanisms created different repeating behaviors. The theories multiplied rapidly. Repeating FRBs effectively shattered the idea that all bursts belonged to one simple category. Instead, astronomers started suspecting an entire population of related phenomena might exist. Some bursts repeat frequently, others rarely, some perhaps never. Some appear inside young star-forming galaxies rich with energetic, massive stars. Others emerge from older, quieter environments where young magnetars should not even exist. The universe once again demonstrated its usual preference for complexity over simplicity. One particularly fascinating aspect of repeating FRBs involves polarization. Radio waves can oscillate in specific directions, and astronomers measure this carefully, because polarization reveals information about magnetic fields near the source and along the signal's journey. Some repeaters showed extreme polarization effects, very extreme. The radio waves appeared twisted dramatically while travelling through intensely magnetized environments. This suggested the bursts originated near objects with colossal magnetic fields. Again, magnetars became leading suspects, especially because magnetars themselves already behave like astrophysical nightmares. These are neutron stars with magnetic fields so powerful they distort nearby matter fundamentally. Their surfaces may crack during magnetic rearrangements, releasing enormous energy bursts, and in 2020, astronomers finally observed something extraordinary inside our own galaxy. A magnetar named SGUR 1935+2154 emitted a powerful radio burst resembling FRBs. For the first time, scientists directly connected magnetars with FRB-like behavior observationally, rather than theoretically. That was a major breakthrough, but not a complete solution, because repeating FRBs still display enormous diversity. Some are far more energetic than the galactic magnetar burst. Others exhibit complex structures not fully explained by existing magnetar models, and a few appear in environments difficult to reconcile with young magnetars entirely. Astronomy often works this way. Each discovery answers one question while creating several new ones immediately afterward. There is also something psychologically fascinating about repeaters specifically. One-time bursts feel like accidents. Repeaters feel intentional somehow. Not literally intentional perhaps, but recurring phenomena naturally trigger pattern recognition in human brains. We instinctively search for rhythm, meaning, and structure. That tendency partly explains why discussions about extraterrestrial intelligence appear constantly around FRBs, despite little evidence supporting such ideas scientifically. Humans hear repeating signals from deep space and immediately become emotionally suggestible. History reinforces this too. When pulsars were first discovered in 1967, their regular pulses seemed so precise that astronomers jokingly labelled them LGM for little green men before neutron star explanations emerged. Repeating FRBs triggered similar emotional reactions in the public imagination. Powerful signals, deep space origins, complex patterns, repeating behaviour. It sounds suspiciously like science fiction. But nature frequently produces phenomena stranger than fiction, without needing intelligent civilizations involved. Pulsars themselves once sounded impossible too. So did black holes. So did gravitational waves. Reality remains perfectly capable of creating bizarre things naturally, and repeating FRBs are certainly bizarre enough already. Another major development came from observing FRBs across broader frequency ranges. Some repeaters emitted bursts spanning huge radio bandwidths, while others behaved differently depending on frequency. This hinted that surrounding plasma environments might shape the signal significantly. Perhaps the bursts themselves begin relatively simply, but become distorted while travelling through magnetized material near the source. Imagine shining a flashlight through turbulent water. The light becomes warped, scattered, stretched. Something similar may happen with FRBs. If true, then the complicated structures astronomers observe partly reflect environments around the sources, rather than only the emission mechanism itself. This possibility excites researchers because it means FRBs can probe otherwise invisible astrophysical regions. The bursts become diagnostic tools, tiny cosmic flashbulbs revealing properties of plasma, magnetic fields, and extreme matter under conditions impossible to reproduce fully on Earth. And the more bursts astronomers collect, the richer the puzzle becomes. Modern observatories now detect repeaters routinely. CHIME alone discovered hundreds of new FRB sources, many repeating unpredictably. Some repeat frequently enough to monitor continuously. Others vanish for months before returning unexpectedly. It almost feels as though the universe enjoys keeping astronomers slightly uncomfortable, which, scientifically speaking, is often productive. The existence of repeaters forced researchers to think more carefully about FRBs fundamentally. Perhaps bursts do not require catastrophic destruction at all. Perhaps they resemble stellar flares or magnetic eruptions instead. Perhaps compact objects store energy gradually before releasing it suddenly under specific conditions, or perhaps multiple classes of FRBs exist simultaneously. That last possibility grows increasingly likely. Astronomy loves categories initially because categories simplify understanding, but reality usually resists neat classification eventually. Stars alone come in enormous varieties, galaxies differ wildly, black holes behave differently depending on environments. Why should FRBs remain simple? Some scientists now suspect repeating FRBs and non-repeating FRBs may represent partially separate phenomena. Others argue they arise from similar objects behaving under different circumstances. The debate continues intensely. Meanwhile, the bursts themselves continue arriving from deep space without explanation. Tiny flashes crossing billions of light years, signals hidden inside radio noise carrying clues about some of the most extreme physics in existence. And there is something wonderfully eerie about the fact that repeating FRBs refuse silence entirely. The universe is not merely producing isolated flashes randomly. Some objects out there are active, persistent, continuing to erupt again and again across cosmic time. If fast radio bursts are among the strangest signals in the universe, then magnetars are among the few objects terrifying enough to plausibly create them. Even astronomers speak about magnetars with a certain cautious respect. Not fear exactly. More the scientific equivalent of looking at an electrical storm through thick reinforced glass and quietly appreciating the fact that it is happening very far away. Because magnetars are violent, exceptionally violent, and they exist under physical conditions so extreme that ordinary intuition stops being useful almost immediately. To understand magnetars properly, we first need to begin with neutron stars, because magnetars are essentially neutron stars pushed to horrifying extremes. When massive stars die, they do not simply fade away peacefully. Gravity eventually wins the long battle against fusion occurring inside the stellar core. Once nuclear fuel becomes exhausted, outward pressure weakens, and the core collapses catastrophically under its own weight. The collapse happens astonishingly fast. Imagine compressing something larger than the Sun into the size of a city in less than a second. Matter itself changes form during this process. Electrons and protons crush together into neutrons. The remaining object becomes unimaginably dense. A neutron star contains roughly the mass of the Sun compressed into a sphere only about 20 kilometers wide. That density is difficult to visualize properly. A teaspoon of neutron star material would weigh billions of tons on Earth. Not metaphorically, literally. One spoonful could outweigh mountains. Fortunately, neutron stars remain far away because keeping one in your kitchen would create practical difficulties. Now, ordinary neutron stars are already extraordinary enough. Some spin rapidly, some emit radiation beams as pulsars, some possess powerful magnetic fields. Magnetars, however, take everything about neutron stars and increase it dramatically, especially the magnetic field. Earth has a magnetic field generated by motions inside its molten core. It protects the planet from solar particles and helps compasses function, which historically prevented sailors from becoming extremely lost quite as often. A refrigerator magnet might produce around 0.01 Tesla. Medical MRI machines may reach several Tesla. the strongest continuous magnetic fields humans can generate in laboratories reach dozens of Tesla. Magnetars operate on levels beyond ordinary comparison. Their magnetic fields can exceed 1 quadrillion Tesla, 10 to the power of 15 Tesla. Numbers like that almost stop feeling real. The magnetic field around a magnetar is so intense it fundamentally alters physics nearby. Atoms become distorted. Electron clouds stretch unnaturally. Vacuum itself may behave strangely under such conditions. If a magnetar passed halfway between Earth and the Moon, its magnetic field could disrupt electronics worldwide instantly. Not because the magnetar intended harm, it would simply exist aggressively. And this immense magnetic energy makes magnetars leading candidates for fast radio burst sources, because FRBs require something capable of storing colossal energy and releasing part of it suddenly in milliseconds. Magnetars qualify beautifully, or perhaps terribly, depending on perspective. The surfaces of neutron stars are solid crusts floating above interiors composed of matter under impossible pressures. In magnetars, magnetic stresses become so extreme they can fracture this crust suddenly. Scientists call these events starquakes, which sounds oddly harmless considering the scale involved. On Earth, earthquakes release energy through shifting tectonic plates. Magnetar starquakes release magnetic energy vastly exceeding anything our planet can produce naturally. During such events, magnetic fields may rearrange violently, accelerating charged particles to incredible energies. Astronomers suspect that under certain conditions these eruptions could generate coherent radio bursts, powerful enough to become FRBs, and for years, magnetars remained mostly theoretical FRB suspects. Then came April 2020. That was the moment the universe handed astronomers one of the most important clues in the entire FRB mystery. Inside the Milky Way exists a known magnetar called SGR 1935+2-154. The name sounds technical because astronomy naming conventions often resemble someone typing angrily at a calculator. Still, this object became historic, because in April 2020, SGR 1935+2154 emitted an extraordinary radio burst. Multiple radio observatories detected it nearly simultaneously, and the burst looked astonishingly similar to fast radio bursts observed in distant galaxies. For the first time, humanity directly witnessed a magnetar producing an FRB-like signal. The excitement across astrophysics was immediate. Years of theoretical work suddenly gained powerful observational support. Magnetars truly could generate FRBs, at least some of them. That last detail matters enormously, because the galactic magnetar burst solved one mystery while leaving several others untouched. The burst from SGR 1935+2-154 was powerful by human standards, absolutely. For a brief moment, it became one of the brightest radio events ever observed inside the Milky Way. But compared with some extragalactic FRBs, it still appeared weaker, much weaker in some cases. That discrepancy raised important questions. Maybe magnetars occasionally produce vastly more powerful eruptions under rare conditions. Maybe younger magnetars behave differently. Or perhaps multiple types of FRB sources exist simultaneously. Astronomy once again refused simplicity. Still, the galactic burst represented a turning point, because suddenly astronomers had a nearby laboratory. Instead of studying FRBs only from billions of light years away, scientists could observe magnetar activity directly inside our own galaxy. And magnetars turned out to be wonderfully chaotic objects. They emit X-rays, gamma rays, magnetic flares, occasional giant eruptions. Their environments are turbulent, energetic and unstable, exactly the sort of astrophysical conditions capable of producing weird radio phenomena. One fascinating idea involves magnetic reconnection. You may already know a gentler version of this process from the Sun. Solar flares occur when twisted magnetic field lines suddenly rearrange. releasing energy explosively. On a magnetar, however, magnetic reconnection becomes vastly more extreme. The fields are stronger, the energy larger, the consequences more violent. Some researchers suspect FRBs emerge when magnetic field lines snap and reconnect near the magnetar surface, launching powerful shock waves through surrounding plasma. As those shock waves travel outward, coherent radio emission may form. That coherence matters critically. FRBs are not random static. The radio waves arrive highly organized, implying huge numbers of charged particles moving together synchronously. Nature somehow coordinates all this under extreme magnetic conditions. Exactly how remains uncertain, and magnetars continue complicating matters. Some magnetars appear relatively quiet for long periods, others erupt unpredictably. Some produce repeated bursts, others behave differently. There is growing evidence that magnetar age may matter too. Young magnetars likely possess especially intense magnetic activity. Fresh supernova remnants surrounding them could shape radio signals significantly. That might explain why many FRBs appear associated with young star-forming regions inside galaxies. Massive stars form there. Massive stars die there. Magnetars emerge there. Still, not all FRBs fit neatly into that picture. A few repeating FRBs originate in older galaxies where fewer young magnetars should exist. Again, the universe refuses clean categories. Perhaps older magnetars remain active longer than expected. Perhaps interactions with nearby companions matter. Perhaps multiple pathways create FRBs. The uncertainty keeps the field exciting and slightly exhausting for theorists. One especially interesting property of magnetars involves rotational energy. Neutron stars spin rapidly because of angular momentum conservation. When a massive stellar core collapses from enormous size into a tiny compact object, rotation speeds up dramatically. It is similar to an ice skater pulling arms inward while spinning, except the skater usually does not become a super-dense magnetic nightmare afterward. Some young magnetars may rotate incredibly fast initially. Combined with strong magnetic fields, this creates enormous available energy reservoirs. Under certain models, FRBs may emerge during early energetic phases of magnetar evolution. Others may occur later through crust fractures or magnetic instabilities. Astronomers continue testing these ideas against observations constantly, and the observations themselves grow increasingly detailed. Modern radio telescopes now capture FRBs with astonishing time resolution. Scientists can study internal burst structures lasting microseconds. Microseconds. That is 1/1,000,000th of a second. Within these tiny windows, bursts display drifting frequencies, subpulses, and intricate patterns hinting at complicated plasma environments near the source. Magnetars naturally produce complicated environments. Their magnetic fields trap charged particles intensely. Radiation interacts with plasma in unusual ways. Shockwaves propagate through magnetized material under conditions impossible to recreate fully in laboratories. This makes magnetars scientifically valuable beyond FRBs themselves. They are natural experiments in extreme physics, general relativity, quantum electrodynamics, plasma physics, nuclear matter, all operating simultaneously under outrageous conditions. Late at night, magnetars almost feel like objects nature invented specifically to remind humanity that the universe still contains things beyond comfortable imagination. Tiny stars smaller than cities, denser than atomic nuclei, spinning rapidly, wrapped in magnetic fields capable of distorting matter itself. And occasionally perhaps firing radio flashes bright enough to cross billions of light years. The emotional scale of that is difficult to process fully. There is also something oddly unsettling about how brief FRBs remain despite originating from such extreme environments. Milliseconds, that is all. After all the violence and magnetic chaos and astrophysical catastrophe involved, the observable burst itself lasts less than a blink. The universe performs these enormous energetic acts with astonishing efficiency. Then silence again. That silence matters too, because magnetars spend most of their existence quiet relative to their explosive moments. They sit in darkness between eruptions like sleeping volcanoes storing stress invisibly. Astronomers monitoring magnetars often wait long periods patiently hoping activity resumes. Sometimes it does dramatically. In 2004, a giant flare from magnetar SGR 1806-20 released more energy in 1/10 of a second than the Sun emits over roughly 100,000 years. The flare briefly affected Earth's ionosphere despite originating around 50,000 light-years away. And that was only gamma-ray emission. Events like these demonstrate how much energy magnetars truly control, enough to plausibly explain at least some FRBs, maybe many, maybe most, but probably not all. Because FRBs continue displaying enormous diversity. Some repeat frequently, others never. Some emerge from environments strongly supporting magnetar models, others appear more difficult to explain. The field remains open, which is one reason as astronomers remain so fascinated. Science becomes most interesting precisely when evidence points strongly in one direction, while still leaving room for surprise. And magnetars certainly leave room for surprise. There comes a point in astrophysics where ordinary language begins struggling to keep up. Stars exploding still feels understandable somehow. Black holes sound dramatic, but familiar now after decades of documentaries and headlines. Even neutron stars, absurdly dense as they are, can still be described using comparisons involving mountains and teaspoons and crushed atoms. Magnetars push beyond that comfort zone, because magnetars do not merely possess strong magnetic fields. They exist inside magnetic violence so extreme that matter itself begins behaving differently. And if fast radio bursts truly come from magnetars, then FRBs may represent moments when this magnetic chaos suddenly tears through space in brief catastrophic eruptions. To appreciate how strange that becomes, we need to talk about magnetic fields themselves first. Because on Earth magnetism feels gentle, useful even. Magnets hold notes on refrigerators, compasses point north, MRI machines scan bodies safely while making noises suspiciously similar to robots falling downstairs. Nothing about everyday magnetism prepares humans emotionally for what magnetars are doing. A magnetic field forms whenever electric charges move. Earth's magnetic field comes from molten ions circulating deep inside the core. The Sun's magnetic field emerges from turbulent plasma motions inside the star. Magnetars take this same basic physics and increase it to levels almost impossible to visualize. Their magnetic fields contain extraordinary amounts of stored energy, and importantly, magnetic fields are not static things. They twist, stretch, tangle, snap, rearrange. Under ordinary conditions, this happens harmlessly. Under magnetar conditions, it becomes cosmic warfare. Imagine twisting thick rubber bands tighter and tighter until eventually they snap violently. Now, replace the rubber bands with magnetic field lines carrying enough energy to power civilizations. That is closer to what scientists suspect occurs around magnetars. The fields become unstable, and when they suddenly rearrange, enormous energy erupts outward. This process is called magnetic reconnection. It already happens on the Sun regularly. Solar flares occur when magnetic fields near sunspots twist together and reconnect explosively. The Sun launches charged particles across the solar system during these events. Earth's magnetic field usually shields us reasonably well, although strong solar storms can still disrupt satellites, communications and power systems occasionally. Magnetars perform similar processes on vastly more terrifying scales. Their magnetic fields become so powerful that they dominate surrounding physics completely. Matter near a magnetar does not behave normally anymore. Atoms distort. Electrons move differently. Vacuum itself may become polarized. That last part sounds fictional, but is entirely real according to quantum electrodynamics. Normally, empty space behaves like empty space. Near a magnetar, however, the magnetic field becomes strong enough to influence virtual particle activity inside the vacuum itself. Light travelling through such regions may split into different polarizations, almost as if empty space turns into a strange crystal-like medium. Nature becomes deeply weird under extreme magnetism, and FRBs may emerge from these environments. One leading idea suggests that sudden magnetic reconnection events launch ultra-fast shockwaves outward through dense plasma surrounding the magnetar. Plasma is often called the fourth state of matter. Instead of solid, liquid, or gas, plasma consists of charged particles moving freely. Stars themselves are mostly plasma. Near magnetars, plasma environments become extraordinarily energetic. When magnetic fields reconnect suddenly, particles accelerate to near-light speeds. Shock waves propagate outward. Electromagnetic energy explodes into surrounding regions. Somehow, under these conditions, coherent radio emission may form. That coherence remains one of the most fascinating parts of the FRB mystery. Ordinary thermal radiation is messy. Particles emit independently in random ways. FRBs are different. Their radio waves arrive highly organized, meaning huge numbers of charged particles emit together in synchronized patterns. Imagine billions upon billions of particles acting almost like a perfectly coordinated orchestra. Exactly how magnetars accomplish this is still debated intensely. Several competing models exist. One proposal involves maser emission inside relativistic shockwaves. A maser is essentially the microwave or radio equivalent of a laser, producing coherent amplified radiation. Under the right plasma conditions, shockwaves around magnetars might naturally generate radio masers powerful enough to create FRBs. Other models suggest coherent curvature radiation from particles moving along twisted magnetic field lines. Still others involve interactions between magnetar winds and surrounding nebulae. The details become complicated quickly because plasma physics under extreme magnetic fields is notoriously difficult. Even supercomputers struggle with these calculations, and nature continues producing results more imaginative than theorists sometimes expect. One especially interesting clue comes from the structure hidden inside repeating FRBs. Remember how some bursts contain drifting subpulses and complex frequency patterns? Those details suggest the radio waves interact with turbulent magnetized environments near the source. A simple explosion in empty space would likely produce cleaner signals. FRBs instead often resemble events filtered through magnetic storms. That matches magnetar environments beautifully, because magnetars are messy. Violent magnetic loops surround them. Dense plasma clouds shift unpredictably. Shock waves interact with surrounding material. The result may naturally create complicated radio structures. Astronomers have even compared some FRB behaviours to processes observed in pulsars and solar radio bursts, though vastly more energetic. There is also the issue of timescales. FRBs last milliseconds. That brevity strongly implies compact sources because larger objects cannot vary brightness so quickly. If something enormous emitted an FRB, different regions would contribute radiation over longer intervals. Magnetars solve this neatly. They are tiny by stellar standards, around 20 kilometers across. A burst occurring near the surface could evolve on millisecond timescales naturally, and magnetars contain enough magnetic energy to power enormous eruptions repeatedly. That matters because repeating FRBs survive. Some sources burst again and again for years. Catastrophic one-time explosions cannot explain that behaviour easily. Magnetars can, at least partially. A magnetar may gradually accumulate magnetic stress before releasing energy episodically through starquakes or reconnection events. Rather than dying during one burst, it remains active, a cosmic pressure cooker venting intermittently. Still, uncertainties remain everywhere. For example, some repeating FRBs display periodic activity cycles. FRB 180916 showed roughly 16-day patterns where bursts appeared during certain intervals before falling silent again. Why? Several possibilities exist. Maybe the magnetar orbits another object, and surrounding plasma blocks burst during parts of the orbit. Maybe precession changes our viewing angle gradually. Maybe magnetic activity itself cycles periodically. No consensus exists yet. And then there are the truly extreme FRBs. Some bursts appear so energetic that even optimistic magnetar models struggle slightly. Not impossibly so, perhaps, but uncomfortably. Scientists may eventually solve this through better understanding of magnetic reconnection efficiency or beaming effects. Or perhaps some FRBs come from entirely different mechanisms altogether. Astronomy rarely rewards single universal explanations for long. One fascinating possibility involves young magnetars specifically. When massive stars explode as supernovas, they may leave behind newborn magnetars spinning rapidly with colossal magnetic fields. These young objects could remain embedded inside expanding supernova remnants filled with turbulent plasma. Such environments naturally explain several FRB properties simultaneously: strong magnetic fields, dense surrounding material, energetic activity, complicated propagation effects. And because young magnetars evolve over time, different ages might produce different FRB behaviors. Younger magnetars may erupt more violently, older ones perhaps less frequently. The theory fits many observations reasonably well, but again, not all. There is another deeply strange aspect to magnetars too. Their magnetic fields may physically deform the stars themselves. The crust experiences enormous stress. Magnetic pressure can crack the surface catastrophically during starquakes. Imagine Earth's crust breaking during earthquakes, except now gravity is vastly stronger, matter denser than atomic nuclei, and magnetic fields capable of altering quantum behavior directly. The energy release becomes almost difficult to conceptualize. In 2004, Magnetar SGR 1806-20 produced a giant flare so powerful that it affected Earth's upper atmosphere despite occurring 50,000 light-years away. For a brief moment, the flare released more energy than the Sun emits over roughly 100,000 years, and even that event may still fall short of the most extreme FRBs, which says something remarkable about the violence potentially involved. Yet despite all, this chaos magnetars remain physically tiny. That contrast feels important somehow. Some of the most powerful phenomena in existence originate from objects smaller than cities. The universe repeatedly demonstrates that compactness and density matter enormously. Black holes, neutron stars, magnetars. Extreme physics loves compression, and perhaps FRBs represent moments when magnetic energy compressed under impossible conditions finally erupts outwards suddenly. Tiny flashes carrying evidence of matter operating at the edge of known physics. Late at night, there is something oddly calming about realizing how far beyond ordinary experience the universe truly extends. Human problems feel large because human scales are small. Meanwhile, somewhere in space, magnetars twist themselves into magnetic catastrophes, powerful enough to distort surrounding plasma, accelerate particles near light speed, and launch radio bursts across galaxies. Reality remains gloriously excessive, and still, magnetars may not even represent the final answer. Some FRBs emerge from environments difficult to reconcile with young magnetars. Others show behaviors current models struggle to reproduce naturally. Science continues because uncertainty remains. That uncertainty is not failure, it is invitation. The universe keeps offering clues while withholding complete explanations, and magnetars stand at the center of that puzzle currently. Violent stellar corpses wrapped in magnetic fields so intense they barely resemble ordinary matter anymore. Every fast radio burst detected on Earth has already survived an impossible journey. That is easy to forget sometimes because astronomers often focus on the source itself: magnetars, neutron stars, extreme magnetic fields, violent eruptions, all fascinating things. But the signal's journey may be just as extraordinary as the object creating it. Because after an FRB explodes outward into space, it does not simply arrive neatly at Earth moments later. It travels, for millions of years sometimes, often billions, across distances so enormous that human history becomes microscopic by comparison. And somehow, after all that time and space and cosmic interference, the signal still reaches our telescopes clearly enough for scientists to study. That alone feels remarkable. Imagine whispering something on one side of an ocean and having someone hear it perfectly on the other side after centuries of storms. FRBs perform cosmic versions of that constantly. To understand how astonishing this really is, we need to begin with one of the strangest facts about the universe itself. Space is not empty. At least not truly. Movies often portray outer space as perfect vacuum, endless black nothingness stretching between stars and galaxies. In reality, even the emptiest regions contain scattered particles drifting through the cosmos. Tiny amounts of gas, electrons, plasma, magnetic fields, dust. The universe is thinly populated almost everywhere, but not completely empty. And over billions of light years, even tiny amounts of material begin to matter. When an FRB erupts from its source, radio waves spread outward in all directions at the speed of light. C is approximately 3 times 10 to the power of 8 meters per second. That speed sounds enormous because it is enormous. Light can circle Earth more than 7 times in 1 second. It reaches the moon in about 1.3 seconds. Sunlight arrives at Earth in roughly 8 minutes, but cosmic distances are so absurdly large that even light begins feeling slow eventually. The nearest star beyond the Sun sits over 4 light years away. The Milky Way spans around 100,000 light years, and many FRBs originate billions of light years from Earth. That means some burst began travelling before multicellular life became common here, before dinosaurs, before forests, possibly before Earth itself looked remotely recognisable. While the signal travels, it crosses vast stretches of intergalactic space filled with extremely thin plasma, and this plasma leaves fingerprints on the burst. One of the most important effects is called dispersion. Dispersion became crucial in FRB science almost immediately, because it provided the first major clue that these signals originated far beyond the Milky Way. The basic idea is surprisingly intuitive. Different radio frequencies travel slightly differently through ionized material. Higher frequencies move more easily. Lower frequencies become delayed slightly during the journey. As a result, when an FRB reaches Earth, the highest frequencies arrive first while lower frequencies trail behind. The burst becomes stretched across time. It is a little like runners separating during a marathon. Everyone starts together, but different speeds gradually spread the group apart over long distances. For FRBs, that stretching becomes measurable, and the amount of dispersion tells astronomers something extraordinary: distance, or more precisely, how much material the signal crossed during its journey. This is one reason FRBs became scientifically valuable so quickly. They are not merely mysterious signals, they are probes travelling through the universe naturally. Each burst carries information about everything it encountered along the way. The larger the dispersion measure, the farther the signal likely travelled and the more matter it crossed. Early FRBs showed enormous dispersion values, far too large for ordinary galactic origins. That is how astronomers realised the burst must come from deep extragalactic space. And once that became clear, the energy calculations turned astonishing. Because if a signal remains detectable after crossing billions of light years, the original burst must have been unimaginably bright. There is another effect too: scattering. As radio waves pass through turbulent plasma regions, they become distorted slightly. The signal may spread out, blur, or flicker in complicated ways. You can think of it somewhat like light passing through fog or rippling water. Intergalactic space itself is mostly thin and calm, but galaxies contain denser plasma environments. Magnetized regions near stars or black holes can scatter radio waves significantly. This means FRBs often arrive carrying traces of the environments they crossed, not just from their source galaxy, not just from intergalactic space, but even from our own Milky Way. Astronomers carefully analyze all these distortions because they reveal otherwise invisible structures spread throughout the cosmos. In fact, FRBs may help solve one of astronomy's long-standing mysteries involving missing baryons. Now that phrase sounds suspiciously like something a fast food restaurant might accidentally serve, but baryons simply refer to ordinary matter made of protons and neutrons. Stars, planets, gas clouds, humans, coffee cups, and slightly overworked astronomers all count as baryonic matter. Cosmological models predict more ordinary matter should exist than astronomers can directly observe. The missing matter likely floats diffusely between galaxies in hot ionized gas difficult to detect otherwise. FRBs help locate it, because every burst crossing intergalactic space becomes dispersed by this hidden material. By measuring enough FRBs across different directions and distances, astronomers can effectively map otherwise invisible matter distributed throughout the universe. Tiny radio flashes become cosmic flashlights. That idea feels wonderfully disproportionate somehow. Signals lasting milliseconds helping humanity study structures spanning billions of light years. FRBs also experience something called Faraday rotation. This occurs when radio waves pass through magnetized plasma environments. The polarization of the waves rotates during travel, and the amount of rotation reveals information about magnetic fields encountered along the way. Some FRBs display enormous Faraday rotation values. That suggests they originated near intensely magnetized environments. Again, magnetars become strong suspects. But the journey itself matters too. Every galaxy crossed, every plasma cloud traversed, every magnetic field encountered leaves subtle marks on the signal. The universe writes on these bursts during transit, and astronomers are learning how to read the handwriting. One especially fascinating aspect of FRB travel involves cosmic expansion. The universe itself expands continuously. Galaxies drift apart over time as space stretches between them. That means FRBs travelling for billions of years do not move through static space. The space itself changes while they travel. As a result, the bursts become redshifted. Their wavelengths stretch gradually during the journey. This effect allows astronomers to estimate enormous distances and study how the universe evolved over cosmic time. An FRB arriving today may carry information from epochs when galaxies were younger and the cosmos itself looked different. In a sense, every FRB is also a time capsule. We never observe the universe as it exists now. Light and radio waves require time to travel. Astronomy always studies the past. FRBs intensify this feeling dramatically because many travelled longer than human civilization has existed. When astronomers detect a burst from billions of light years away, they observe an event that occurred billions of years ago. The source itself may have changed completely since then. Perhaps the magnetar no longer exists. Perhaps the entire galaxy evolved dramatically. Maybe civilizations appeared somewhere during the signal's journey and vanished again before Earth even received the burst. The scale of cosmic time quietly overwhelms ordinary intuition, and still the signal arrives. That reliability is partly because radio waves travel efficiently through space. Unlike visible light, radio frequencies can pass through dust clouds relatively easily. Intergalactic space, while not empty, remains thin enough that radio signals survive long journeys remarkably well. If FRBs emitted primarily visible light instead, many would become obscured long before reaching Earth. Radio astronomy gives humanity access to hidden layers of the universe precisely because radio waves endure. There's also something strangely emotional about imagining these journeys physically. Picture a burst erupting near a distant magnetar. The radio waves explode outward across the host galaxy. They pass stars and nebulae, cross galactic halos, escape into intergalactic darkness. Then for billions of years the signal travels through expanding space completely alone. No sound, no interruption, just electromagnetic waves moving steadily across unimaginable emptiness. Eventually the Milky Way drifts into the signal's path. The burst enters our galaxy, crosses diffuse plasma between the stars, passes silently through Earth's atmosphere, strikes a radio telescope, and for less than a heartbeat, humanity notices it. There is something deeply beautiful about that sequence, a tiny connection formed briefly across billions of years and billions of light years. And despite all the distance involved, FRBs remain astonishingly precise scientifically. Modern telescopes can localize some bursts to specific galaxies with incredible accuracy. Arrays like CHIME, ASCAP, and the Deep Synoptic Array now detect FRBs routinely and trace them back to host environments across the observable universe. Each localization reveals new clues: young galaxies, old galaxies, dense star-forming regions, unexpected environments. The burst continues surprising astronomers, and the farther they travel, the more useful they become for cosmology itself. Some researchers hope FRBs may eventually help measure the universe's expansion more precisely. Others want to use them for mapping cosmic magnetic fields or studying intergalactic turbulence. A few even speculate FRBs could become tools for probing dark matter indirectly if certain interactions affect radio propagation subtly. The possibilities keep growing, which is fitting, because FRBs themselves spent most of cosmic history unnoticed. Signals crossing the universe silently while humanity evolved from simple organisms into a technological civilization capable of hearing them. Late at night, there is something calming about realizing how temporary our perspective really is. Human lives feel long from the inside, but compared with FRB journeys, entire civilizations become brief flickers. These bursts began travelling long before our species understood stars at all, and long after current cities vanish someday, radio waves from distant galaxies will still continue crossing intergalactic darkness patiently. The universe operates on scales far larger than human urgency, and somehow, despite all the chaos and distance involved, tiny millisecond signals still find their way here. One of the strangest things about fast radio bursts is that astronomers became excited about them even before understanding what they actually are. Usually science works the other way around. First, researchers identify an object, then they study it carefully. Eventually, practical uses emerge afterward. FRBs skipped several steps in that process. The signals arrived so unexpectedly and carried such unusual properties that scientists quickly realized they might become incredibly useful long before the mystery itself was solved. And in astronomy, usefulness often matters just as much as explanation, because the universe contains enormous things humanity still cannot see directly, not because they are invisible in some magical sense, but because they are too thin, too diffuse, or too distant for ordinary observation methods. FRBs may help change that. Tiny flashes lasting milliseconds could become some of the best tools humans have ever developed for mapping the hidden structure of the cosmos itself, which feels wonderfully disproportionate, a signal shorter than a blink helping reveal the architecture of the universe. To understand why FRBs became so valuable scientifically, we need to return to dispersion again. That effect turned out to be far more important than astronomers initially realized. Remember, radio waves traveling through ionized material become stretched because lower frequencies slow slightly relative to higher frequencies. The amount of stretching depends on how much plasma the signal crosses. That means every FRB carries a built-in record of the invisible matter encountered during its journey. And because many FRBs travel across billions of light years, they pass through enormous amounts of intergalactic space. That is where things become fascinating. Most ordinary matter in the universe does not exist inside stars. That surprises people sometimes because stars dominate astronomy visually. They're bright, dramatic, and emotionally persuasive. But stars actually account for only a small fraction of ordinary matter overall. Much of the universe's normal material drifts thinly between galaxies: hot gas, diffuse plasma, extremely sparse particles scattered across cosmic voids. And for decades, astronomers struggled to detect all of it directly. This became known as the missing baryon problem. Again, baryons simply means ordinary matter built from protons and neutrons. Humans are baryons, planets are baryons, sandwiches are baryons. The universe appears strongly committed to baryons generally. According to cosmological models and observations of the early universe, a certain amount of ordinary matter should exist today. But when astronomers counted stars, galaxies, and observable gas clouds, a significant fraction appeared missing. Not dark matter, ordinary matter, just hidden somehow. Researchers suspected the missing material existed in diffuse intergalactic plasma too faint and spread out to observe easily. FRBs suddenly provided a way to detect it. Every burst crossing intergalactic space becomes dispersed by this hidden plasma. The farther the signal travels and the more matter it encounters, the larger the dispersion measure becomes. So by studying FRBs from many different distances and directions, astronomers can estimate how much material exists between galaxies. It is a little like shining flashlights through fog at night. By observing how the beams become distorted, you can estimate the thickness and structure of the fog itself. FRBs perform cosmic versions of this naturally, except the flashlight is a millisecond radio burst from another galaxy, and the fog spans billions of light years. One especially important breakthrough came in 2020, when astronomers successfully used FRBs to locate significant portions of the universe's missing baryonic matter. The results strongly supported the idea that much ordinary matter exists spread thinly throughout intergalactic space exactly as predicted. That was a huge success for cosmology. Tiny radio flashes had helped solve a major large-scale cosmic mystery. There is something deeply satisfying about that scientifically. The universe often hides enormous truths inside very small clues, but FRBs can reveal much more than missing matter. They also help astronomers study cosmic magnetic fields. Magnetic fields exist everywhere in the universe, around stars, inside galaxies, between galaxies, around black holes, across clusters of galaxies. Yet magnetic fields are notoriously difficult to map directly because they are invisible themselves. Scientists usually infer their existence indirectly through effects on charged particles or electromagnetic waves. FRBs are excellent for this. As radio waves travel through magnetized plasma, their polarization rotates. This effect is called Faraday rotation. The stronger the magnetic fields and denser the plasma, the larger the rotation becomes. By measuring polarization changes carefully, astronomers can estimate magnetic conditions along the FRB's path. This allows researchers to probe environments impossible to study otherwise. Some FRBs show enormous Faraday rotation values, suggesting they originate near intensely magnetized objects such as magnetars or active galactic environments. Others appear relatively calm. Each burst becomes a diagnostic tool, a tiny probe launched accidentally by the universe itself. FRBs may even help map the cosmic web. Now, the cosmic web is one of the most beautiful large-scale structures in astronomy, although beautiful here mostly means astonishingly gigantic and faint. Galaxies are not distributed randomly through space. Instead, they form enormous filaments stretching across the universe like strands of an immense three-dimensional network. Between these filaments lie vast cosmic voids where relatively little matter exists. The structure resembles foam or spiderwebs on unimaginable scales. Most of the ordinary matter in the universe likely traces these filaments, but directly observing the gas inside them remains difficult because it is thin and dim. FRBs crossing the cosmic web become dispersed differently, depending on how much material they encounter along various paths. By collecting thousands or eventually millions of FRB observations, astronomers may build increasingly detailed maps of matter distribution throughout the observable universe. In other words, FRBs may allow humanity to illuminate the invisible scaffolding holding galaxies together across cosmic distances, and the bursts accomplish this while lasting milliseconds. That still feels wonderfully excessive somehow. The universe loves hiding enormous significance inside tiny events. There are even more ambitious possibilities too. Some scientists hope FRBs might eventually improve measurements of cosmic expansion itself. Because the universe expands continuously, galaxies drift apart over time. Understanding exactly how fast this expansion occurs matters enormously for cosmology. Different measurement techniques currently produce slightly conflicting answers for the expansion rate, a disagreement known as the Hubble tension. FRBs might help resolve some of these uncertainties eventually by providing independent distance measurements across vast cosmic scales. That possibility excites researchers tremendously, because the Hubble tension may hint at new physics hidden inside cosmology itself. Again, FRBs become tools before becoming fully understood objects. Astronomy sometimes works beautifully that way. There is another reason FRBs are useful too. They are everywhere, or at least surprisingly common. Once instruments improved enough, astronomers realize the universe likely produces thousands of FRBs every day across the observable cosmos. Most go undetected simply because telescopes are not looking in the right direction at the right moment, but future observatories may detect enormous numbers continuously. Projects like CHIME already revolutionize the field by discovering huge populations of bursts rapidly. Future instruments such as the Square Kilometre Array could transform FRB science even further. Imagine a future cosmic weather map built partly from FRBs. Tiny signals tracing hidden plasma, measuring magnetic fields, revealing galaxy halos, illuminating intergalactic structure, all from millisecond radio flashes crossing billions of light years. One particularly interesting development involves localized FRBs. When astronomers pinpoint bursts precisely to specific galaxies, they gain enormous additional information. They can compare dispersion measures with galaxy distances directly. They can study host galaxy environments. They can estimate how much material exists between Earth and the source more accurately. This turns FRBs into precise cosmological rulers of sorts. Each localized burst becomes another probe through the invisible universe, and the environments themselves often surprise scientists. Some FRBs originate in young star-forming galaxies filled with energetic stellar activity. Others emerge from older, quieter galaxies. Some repeat frequently, others never. This diversity suggests FRBs may arise from multiple astrophysical pathways simultaneously, but regardless of their origins, the signals remain scientifically valuable because of the journeys they undertake. Every FRB crossing intergalactic space gathers information naturally along the route. In some ways, the universe performs the experiment for us. Humanity merely listens carefully afterward. There is something emotionally beautiful about that arrangement. Astronomers do not need to build giant probes capable of travelling billions of light years. The cosmos already sends signals through itself constantly. FRBs become messengers carrying environmental information across impossible distances. And because the signals are so bright in radio wavelengths, they survive journeys many other forms of radiation could not. Visible light gets blocked by dust more easily. X-rays require special energetic environments, but radio waves travel efficiently through much of space. That durability makes FRBs exceptionally useful for cosmological studies. Some researchers even wonder whether FRBs might help study dark matter indirectly someday. Dark matter itself remains invisible because it does not interact with light normally. Scientists infer its existence through gravity. Still, if dark matter affects plasma distributions or electromagnetic propagation subtly under certain conditions, huge FRB datasets might eventually reveal patterns impossible to detect otherwise. That remains speculative for now. But FRB science is still young, very young. Humanity discovered the first FRB only in 2007. Compared with centuries of optical astronomy, the field barely exists yet historically. And already these bursts are helping solve major cosmological problems. That fact alone suggests the next few decades may become extraordinary. Because every improvement in observation technology reveals new layers of complexity. Better radio arrays detect more bursts. Higher time resolution reveals finer structures. Improved localization identifies more host galaxies. Machine learning systems uncover patterns humans might miss entirely. The invisible universe slowly becomes less invisible. Late at night, there is something comforting about realizing how much of reality remains hidden, yet still discoverable. Human beings evolved beneath ordinary skies without knowing galaxies existed, without knowing black holes existed, without knowing space-time itself could ripple through the cosmos. Now, tiny radio flashes from billions of light-years away help humanity map matter spread across the universe itself. The scale of intellectual progress feels almost surreal sometimes, and still, the cosmos keeps offering more mysteries. By the time astronomers confirmed fast radio bursts were real, the theories began multiplying almost immediately. That happens whenever science encounters something both powerful and poorly understood. Human imagination rushes in to fill the gaps. Some ideas turn out sensible, others become ambitious, and a few sound like they escaped from late-night science fiction marathons after everyone involved consumed too much coffee and stopped sleeping responsibly. FRBs inspired all of them, partly because the bursts themselves seemed unreasonable at first. Tiny flashes from distant galaxies, milliseconds long, powerful enough to outshine entire galaxies in radio wavelengths, sometimes repeating, sometimes silent forever, and often behaving in ways no known object explained cleanly. When nature produces something strange, theorists become wonderfully creative. Astronomy entered a period where papers appeared proposing everything from collapsing neutron stars to alien engines larger than planets. And technically speaking, many of those ideas were at least mathematically possible. That is the dangerous thing about theoretical astrophysics sometimes. The universe is weird enough that extremely strange ideas occasionally survive serious scientific consideration longer than anyone initially expects. One of the earliest proposals involved evaporating black holes. This idea came partly from Stephen Hawking's famous prediction that black holes slowly lose mass through quantum effects now called Hawking radiation. According to the theory, black holes are not completely eternal. Tiny black holes especially could gradually evaporate over immense timescales, and near the very end of their existence they might release sudden bursts of energy. Some researchers wondered whether FRBs represented final explosions from primordial black holes left over from the early universe. The concept sounded dramatic enough, certainly. Ancient black holes dying in brief flashes after surviving since near the beginning of time itself. There was just one problem. The numbers became awkward. Observed FRB energies and repetition patterns did not fit neatly with simple evaporation models. Repeating bursts especially complicated the idea immediately because evaporating black holes do not get second chances. Once exploded, they remain impressively unavailable for future observations, so the theory gradually lost popularity. Still, for a while, humanity seriously entertained the possibility that FRBs were dying black holes whispering final messages across the cosmos, which already sounds like science fiction. Then things became stranger. Some theorists proposed cosmic strings. Cosmic strings are hypothetical defects in space-time itself, possibly formed during the early universe. Imagine cracks appearing while ice freezes across a pond, except now replace the pond with space-time shortly after the Big Bang. These objects, if they exist, would contain extraordinary energy. Tiny segments vibrating or colliding might release bursts detectable across the universe. FRBs briefly became possible cosmic string candidates because the bursts were short, energetic, and mysterious enough to accommodate exotic explanations. The universe, after all, contains many things once considered absurd. Black holes sounded ridiculous initially. So did neutron stars. So did expanding space-time. Astronomers try to remain careful about dismissing weird possibilities too quickly. Reality has embarrassed scientific certainty many times before. Still, cosmic strings remain speculative. No direct evidence confirms their existence currently, and FRBs increasingly appeared linked with magnetar-like environments observationally. The theory faded somewhat, though not completely. There are always physicists somewhere quietly keeping strange ideas alive just in case the universe decides to become even less reasonable later. Then came the extraterrestrial civilization theories. These received enormous public attention for obvious reasons. Mysterious repeating radio bursts from deep space naturally trigger human imagination almost automatically. History prepared us for this reaction too. When pulsars were discovered in 1967, astronomers jokingly labelled them LGM for little green men because the signals seemed unnervingly regular at first. FRBs produce similar emotional responses, especially repeaters. A signal repeating from deep space sounds suspiciously intentional to human brains even when it probably is not. One particularly famous proposal came from Harvard astronomer Avi Loeb and Manasvi Lingam, who explored whether FRBs could theoretically originate from giant artificial transmitters. Importantly, they did not claim FRBs actually were alien technology. That distinction often disappears online immediately afterward, unfortunately. Instead, they examined whether the energy requirements might allow advanced civilizations to generate such signals intentionally. The hypothetical concept involved enormous beamed energy systems, perhaps used for powering light sails or interstellar spacecraft. Under this scenario, FRBs might represent leakage from gigantic energy infrastructures. The scale required was extraordinary. Planet-sized transmitters, immense power generation, civilizations far beyond current human capability. And again, the paper did not argue this explanation was likely, only physically conceivable. Still, once alien megastructures enter public discussion, subtle nuance tends to die very quickly. Suddenly headlines everywhere announced possible alien origins for FRBs. Astronomers everywhere sighed collectively. Because science communication becomes complicated whenever extraterrestrials appear. Most researchers remain cautious about alien explanations, not because intelligent life elsewhere seems impossible, but because nature consistently produces strange natural phenomena without needing civilizations involved. Pulsars once seemed artificial, quasars once seemed impossible, gamma-ray bursts once baffled astronomers too. The universe does weird things naturally all the time, and magnetars already provide reasonably plausible FRB mechanisms without requiring galaxy-spanning alien engineering projects. Still, the alien theory persists culturally because FRBs feel emotionally uncanny. Brief repeating signals from deep space naturally resemble the sort of thing humans expect intelligent civilizations might produce, especially late at night when imagination becomes more active and rational, skepticism slightly sleepier. There were even proposals involving dark matter interactions. Dark matter remains one of the greatest unsolved mysteries in physics. Scientists know it exists gravitationally because galaxies rotate too quickly, and large-scale cosmic structures behave strangely otherwise. But nobody knows exactly what dark matter is. Some theorists wondered whether interactions between dark matter clumps and neutron stars might trigger FRB-like events. Others proposed axions, hypothetical particles possibly related to dark matter, converting into radio waves near strong magnetic fields. These ideas remain speculative but scientifically interesting because FRBs involve conditions extreme enough to probe unusual physics. That is part of what makes them so exciting theoretically. They operate near the edges of known astrophysics. And whenever science reaches boundaries like that, new possibilities emerge naturally. One especially unsettling theory involved blitzers. This concept sounds fictional enough already. A blitzer would be a neutron star temporarily surviving collapse into a black hole, because rapid rotation provides extra support against gravity. Eventually, as the star loses rotational energy, the support weakens suddenly. Collapse follows, and during that collapse, the star's magnetic field disconnects violently, potentially generating a fast radio burst. The name itself sounds like a comic book villain, but the physics behind it is serious. Blitzer models elegantly explained non-repeating FRBs, because the source destroys itself during collapse. Unfortunately, repeating FRBs complicated things again. The universe apparently enjoys ruining elegant theories through inconvenient observations. Some researchers proposed interactions between neutron stars and orbiting companions, perhaps asteroids, perhaps planets, perhaps white dwarfs. As material moved through magnetized environments around compact objects, radio bursts might emerge periodically. Others suggested binary magnetar systems producing complicated magnetic interactions. There were even ideas involving collapsing strange quark stars. Now, strange quark matter deserves a brief pause because it sounds deeply suspicious at first. Ordinary matter contains protons and neutrons built from quarks. Under sufficiently extreme densities, theorists speculate matter might transition into exotic states involving free quarks moving collectively. Hypothetical strange quark stars could consist of this ultra-dense exotic matter, and if such objects exist, perhaps they generate unusual radio bursts under catastrophic conditions. Again, FRBs became magnets for speculative physics, because the observations were so difficult to explain neatly. Even now, despite growing evidence supporting magnetars strongly, theorists continue exploring alternatives because several FRB properties remain puzzling. For example, some repeating FRBs display periodic activity cycles. Why? Some bursts exhibit incredibly complex frequency structures. Why? A few appear associated with environments difficult to reconcile with young magnetars entirely. Again, why? Astronomy rarely settles completely after first explanations emerge. Reality tends to contain layers underneath. There is another reason FRBs encouraged unusual theories too. Energy concentration. The burst compresses. Enormous power into milliseconds. Human intuition dislikes that. The scale feels wrong emotionally. Even scientists experience this reaction sometimes when calculations first emerge. Numbers become so extreme that ordinary reasoning briefly hesitates. Surely nothing natural behaves like this, and then nature calmly continues behaving exactly like this anyway. That tension between intuition and reality drives much theoretical creativity. Some of the stranger FRB ideas emerged precisely because researchers tried thinking beyond ordinary astrophysical assumptions. Could unknown plasma instabilities create coherent radio emission somehow? Could black hole magnetospheres generate bursts? Could entirely new classes of compact objects exist? Could quantum vacuum effects matter near magnetars? Under sufficiently extreme conditions, known physics itself becomes difficult to test experimentally. That leaves room for surprises, and FRBs operate under extremely extreme conditions. There is something deeply human about this entire process. The moment humanity encounters unexplained signals from deep space, imagination expands outward rapidly. Some people envision alien civilizations, others imagine exotic physics. Some hope FRBs reveal entirely new cosmic structures. Science itself advances partly through this creative stage. Most ideas fail eventually. A few survive. Occasionally one changes understanding permanently. The important thing is that nature decides eventually, not preference. Observations rule, and observations increasingly point toward magnetars for many FRBs, but perhaps not all. that uncertainty keeps theoretical possibilities alive. One especially fascinating development involves the realization that FRBs themselves may not represent a single phenomenon. Instead, there may be families of related events produced through different mechanisms. Some repeat frequently, some never repeat. Some emerge from young star-forming galaxies. Others appear in older environments. Some bursts display intricate drifting structures. Others look simpler. Maybe humanity grouped several distinct phenomena together under one label accidentally because they appear superficially similar. Astronomy has done this before. For years, gamma-ray bursts seemed like one mysterious category, until researchers eventually realized multiple types existed with different origins. Perhaps FRBs follow similar patterns. If true, then several currently competing theories might all be partially correct simultaneously. That possibility feels very realistic scientifically. Nature rarely limits itself to single mechanisms elegantly matching human classification systems. Late at night, there is something oddly comforting about how much uncertainty still surrounds FRBs. Not frustrating, comforting. The universe remains unfinished intellectually. Humanity still lives inside a cosmos capable of generating entirely new mysteries. And even the strangest theories reveal something important about science itself. Scientists are willing to consider astonishing possibilities when evidence demands it. Not because researchers are irrational, quite the opposite. Reality itself repeatedly proves stranger than intuition first allows. So theorists continue exploring possibilities carefully. Magnetars, black holes, exotic matter, cosmic strings, unknown plasma physics, and yes, occasionally even alien engineering projects larger than planets. Because somewhere beyond the stars, fast radio bursts continue appearing without fully explaining themselves. Tiny flashes carrying clues through billions of light years, and each new burst reminds humanity that the universe still contains phenomena strange enough to blur the line between astrophysics and science fiction. One of the most fascinating things about fast radio bursts is that they began as a mystery about strange signals, but slowly transformed into something much larger. A tool, a measuring stick, a way of studying the universe itself. That shift happens often in astronomy. Humans discover something confusing, spend years trying to understand it, and eventually realize the mystery can also help answer entirely different questions. Black holes began as mathematical curiosities. Pulsars began as unexplained radio signals. Supernovas became cosmic distance markers. And now FRBs are becoming instruments for studying time, distance, matter, and the large-scale structure of reality itself, which is remarkable considering these bursts last only milliseconds. There is something almost humorous about that imbalance. Human civilization built giant radio observatories across deserts and mountains, connected them to supercomputers, trained machine learning systems to search for invisible flashes from deep space, and after all that effort, the signals themselves still vanish faster than a blink. And yet inside those tiny bursts lies information about billions of years of cosmic history. Because FRBs are not just events, they are travellers. Every burst reaching Earth has crossed enormous distances through an evolving universe. The signal carries traces of that journey inside it, almost like cosmic fingerprints pressed into radio waves. And by learning how to read those fingerprints, astronomers are beginning to study the universe in ways that were almost impossible before. The first major lesson, FRBs, taught humanity was about scale. Not emotional scale, literal scale. Distances so large that ordinary language struggles to describe them naturally. Human beings evolved on a small rocky planet orbiting one average star. Our instincts understand walking distances, driving distances perhaps, maybe even planetary scales if we work hard mentally. Cosmic distances are something else entirely. Light itself, moving at roughly 300 million meters per second, requires years just to reach nearby stars. c is approximately 3 times 10 to the power of 8 meters per second, and many FRBs travel not for years, not for centuries, but for billions of years before arriving at Earth. That means every FRB is ancient. When astronomers detect a burst tonight, the event itself may have happened before complex animals existed here. Some FRBs began travelling long before dinosaurs. Others started their journeys before Earth looked remotely familiar. The burst itself may have crossed the universe while continents drifted, species evolved, and civilizations rose and vanished entirely. And after all that time, the signal arrives at a radio telescope for a few milliseconds. Then it disappears forever. There is something deeply strange about that sequence emotionally. Humans usually experience time locally. Minutes feel real. Days feel meaningful. Years feel long. The universe barely notices years. FRBs quietly force astronomers to think in cosmic time instead. A signal travelling for billions of years becomes a message from a completely different epoch of the universe. Because the cosmos itself changes over time. Galaxies evolve, stars die, new stars form, black holes grow, space expands continuously. That last part matters enormously. The universe is not static. Ever since the Big Bang, space itself has been stretching. Galaxies drift apart not because they move through space like airplanes across skies, but because the space between them expands. This means FRBs travel through a changing universe during their journey. And because of that expansion, the bursts become red-shifted. Their wavelengths stretch gradually while crossing cosmic distances. This effect allows astronomers to estimate distances and study how the universe evolved over time. In a sense, every FRB becomes a probe of cosmic history. The farther away the source, the farther back in time humanity sees. Astronomy always works this way technically. Looking into space means looking into the past because light requires time to travel. But FRBs intensify this feeling dramatically because the distances involved are so extreme. The signals become reminders that human civilization occupies only a tiny fraction of cosmic history. Late at night, that realization can feel oddly calming. Many everyday worries depend on the illusion that the present moment is enormous. The universe gently disagrees, and yet, despite those impossible distances, FRBs still remain detectable. That alone reveals something important about the structure of the cosmos, because the signals survive. They cross billions of light years through intergalactic plasma, magnetic fields, galaxy halos, and expanding space-time itself while preserving enough information for astronomers to analyze afterward. That survival allows scientists to measure invisible matter spread throughout the universe. Remember the missing boron problem from earlier. Astronomers knew ordinary matter should exist in larger quantities than observations directly revealed. Much of it likely floated diffusely between galaxies in thin hot plasma. FRBs solved part of that mystery beautifully. Every burst becomes dispersed while travelling through ionized matter. Lower frequencies slow slightly relative to higher frequencies, stretching the signal in measurable ways. The more matter encountered, the greater the dispersion. By measuring enough FRBs, astronomers can estimate how much hidden material exists between galaxies. That is extraordinary when you stop and think about it. A burst lasting milliseconds helps humanity map invisible matter spread across billions of light years. Tiny signals revealing gigantic structures. The universe often works through disproportion like that. One especially fascinating implication of FRBs involves the cosmic web. Galaxies are not scattered randomly through space. Instead, they form enormous filaments stretching across the universe like strands inside a gigantic three-dimensional network. Between these filaments lie vast voids where relatively little matter exists. The structure resembles foam or spiderwebs on unimaginable scales. Most ordinary matter likely traces this cosmic web, but much of that matter is too diffuse to observe directly. FRBs crossing the universe become probes of the web itself. Signals travelling through dense filament regions become dispersed differently than signals crossing emptier voids. Eventually, with enough FRB detections, astronomers may map intergalactic structure in astonishing detail. Humanity could effectively illuminate invisible cosmic scaffolding using radio flashes from distant galaxies. That sentence would have sounded absurd 50 years ago. Now it is active astrophysical research. FRBs also reveal something profound about magnetic fields on cosmic scales. Magnetic fields exist everywhere in the universe, but they remain difficult to observe directly. Stars possess magnetic fields. Galaxies do too. Even intergalactic space contains faint magnetic structures. When FRBs travel through magnetized plasma, the polarization of their radio waves rotates through something called Faraday rotation. By measuring this carefully, astronomers estimate magnetic conditions along the signal's path. Some FRBs display enormous Faraday rotation values, suggesting highly magnetized environments near their sources. Others reveal subtler structures spread across intergalactic space. Again, tiny bursts become measurement tools for enormous invisible systems. The signals are almost like cosmic sonar. Humanity sends nothing outward. Instead, the universe naturally provides flashes crossing vast distances, and scientists interpret the distortions afterward. There is another deeply interesting aspect to FRBs too. They reveal how incomplete human perception naturally is. For most of history, humans had absolutely no awareness that these signals existed. The sky looked quiet. Stars moved slowly. Galaxies glowed faintly through telescopes. Meanwhile, FRBs crossed the universe constantly unnoticed. Only recently did technology become advanced enough to detect them. That realization matters philosophically as much as scientifically. Reality always contains more than humans perceive directly. Before radio astronomy, pulsars were invisible. Before X-ray telescopes, black hole accretion disks remained hidden. Before gravitational wave detectors, colliding black holes pass silently through the universe unheard. FRBs remind humanity that the cosmos still contains layers waiting to be discovered. Perhaps entire categories of phenomena remain invisible simply because current instruments cannot detect them yet. Future civilizations may look back at modern astronomy the way modern astronomy looks back at ancient stargazing, respectfully perhaps, but aware that enormous pieces of reality remained hidden. There is also something emotionally powerful about the way FRBs connect space and time together. The farther away a burst originates, the older the universe appears during observation. A nearby FRB reveals relatively recent cosmic history. A distant FRB reveals ancient epochs from when galaxies were younger and the universe itself denser. This means FRBs help astronomers study not only where matter exists, but how cosmic structures evolved over billions of years. Some bursts may even emerge from periods when star formation across the universe behaved differently than today. Others crossed regions altered dramatically by galaxy mergers or black hole activity during their journey. Each signal carries history inside it. And perhaps most importantly, FRBs remind humanity how astonishingly interconnected the cosmos truly is. A magnetic eruption around a compact object in a distant galaxy affects scientific understanding on Earth billions of years later. Tiny events propagate across cosmic distances and cosmic time. Reality is not isolated pieces floating separately. It is one continuous evolving system connected through physics, radiation, gravity, and space-time itself. That thought becomes especially striking late at night. Human beings often feel isolated emotionally because daily life narrows attention to immediate surroundings. But FRBs quietly demonstrate that events occurring unimaginably far away can still reach us eventually. The universe remains connected across scales beyond ordinary comprehension, and all of this scientific insight emerged from signals humanity nearly ignored initially. The first FRB sat buried in archived telescope data for years before anyone recognized its significance. Now entire observatories scan the heavens, continuously searching for more. Projects like CHIME detect huge numbers routinely. Future telescopes, such as the Square Kilometre Array, may revolutionize the field entirely. Researchers hope eventually to use FRBs for precision cosmology, measuring universal expansion, mapping intergalactic plasma, studying galaxy halos, tracing magnetic structures, perhaps even investigating dark matter indirectly someday. The possibilities keep growing because the bursts themselves cross so much of the universe before reaching Earth. Every journey becomes data. Every distortion becomes information. Every burst becomes a tiny cosmic messenger, carrying evidence about time, distance, matter, and the structure of space-time itself. And still, despite all the science involved, there remains something quietly emotional about the image of FRBs travelling through darkness for billions of years. A signal erupts near a magnetar perhaps no larger than a city. The radio waves escape the host galaxy, cross cosmic voids, travel through expanding space longer than human civilization has existed. Eventually, Earth drifts into the signal's path. A radio telescope notices a brief disturbance. Astronomers decode hidden information inside the burst. And for a tiny moment, humanity connects with an event that happened billions of years ago in another corner of the universe. The scale of that connection feels almost impossible, yet it happens constantly now. Somewhere tonight, another fast radio burst is already travelling through the universe, not metaphorically, not eventually, right now. At this exact moment, while cities glow beneath clouds and people fall asleep beside windows and distant highways hum quietly in the background, a tiny pulse of radio energy may already be crossing intergalactic darkness toward Earth. It began long ago, long before this video, long before modern astronomy, possibly before human civilization itself. Somewhere in a distant galaxy, under conditions still not fully understood, an extreme object released a sudden burst of energy into space. Maybe a magnetar twisted itself into magnetic chaos. Maybe a neutron star cracked beneath unimaginable stress. Maybe plasma erupted outward through fields stronger than anything humanity can reproduce. And then the signal left. A few milliseconds, that was all. A brief flash of radio energy expanding outward at the speed of light. C is approximately 3 times 10 to the power of 8 meters per second. The burst crossed its host galaxy first, past stars, dust clouds, nebulae, perhaps even planets orbiting suns that will never know the signal existed. Then it escaped into intergalactic space, and for billions of years it travelled, silently, crossing enormous cosmic voids where galaxies become sparse and distances lose, ordinary meaning, passing through thin plasma spread invisibly across the universe, sliding through magnetic fields stretched between galaxies themselves. While the signal travelled, entire histories unfolded elsewhere. Stars formed and died, black holes grew, galaxies collided. On Earth, species evolved slowly across oceans and continents. Dinosaurs appeared, vanished, mammals spread, humans emerged, learned language, built cities, invented telescopes, began asking questions about the stars, and all the while that tiny radio pulse kept moving steadily through darkness. There is something strangely emotional about that idea. Not sad exactly, not hopeful either, just vast. Human life feels busy from the inside because our timescales are small. Days matter enormously to us. Years feel significant. Entire civilizations seem permanent while we are living inside them. FRBs quietly reveal a larger perspective. A signal can spend longer travelling across the universe than human civilization has existed, and still arrive precisely on time according to physics. Astronomy does this repeatedly. It rearranges scale gently until ordinary assumptions stop feeling stable. The night sky once looked simple, tiny lights overhead, predictable patterns. Ancient people imagined constellations, myths, gods, stories. Now humanity understands that hidden inside the darkness are black holes bending space-time, galaxies colliding over millions of years, neutron stars denser than atomic nuclei, and mysterious radio bursts powerful enough to outshine galaxies briefly before vanishing again. The universe became stranger the closer humans looked, and somehow also more beautiful. Because reality turned out not to be empty silence. It crackles with activity. Invisible radiation crosses space constantly. Pulsars rotate like giant clocks. Quasars roar from galactic centers. Gravitational waves ripple through space-time from black hole collisions, and FRBs flash suddenly through the cosmos like brief cosmic sparks. For most of history, humanity had no idea these signals existed. That fact alone feels important. FRBs crossed the universe unnoticed while empires rose and collapsed. They passed Earth silently during ancient history, through medieval nights, through wars and discoveries and generations of people staring upward, without realizing invisible bursts were moving overhead constantly. Only recently did technology become sensitive enough to hear them, and once humanity started listening properly, the universe sounded much stranger than expected. That pattern repeats throughout science. Every improvement in observation changes reality slightly. Microscopes revealed hidden worlds inside droplets of water. Telescopes revealed galaxies beyond the Milky Way. Radio astronomy revealed pulsars and quasars. Gravitational wave detectors revealed space-time itself vibrating. FRBs remind humanity that discovery is not finished. The cosmos still contains surprises, perhaps enormous ones. There may be entire categories of astrophysical phenomena humanity has not recognized yet, simply because our instruments remain incomplete. Future civilizations may detect things modern astronomy cannot even imagine currently. That thought feels oddly comforting late at night. Reality remains alive with unanswered questions, and unanswered questions are wonderful things, because they leave room for curiosity. FRBs also change how astronomers think about the universe itself. What began as a mystery about strange radio flashes became a tool for studying invisible matter, cosmic magnetic fields, intergalactic plasma, and the large-scale structure of space-time. Tiny signals became cosmic probes. That transformation says something beautiful about science. Sometimes confusion itself becomes useful. Humanity did not fully understand FRBs before using them to study the cosmos. The burst arrived carrying information hidden inside them naturally. Scientists simply learned how to interpret the distortions. Dispersion revealed invisible matter between galaxies. Polarization revealed magnetic fields. Distances revealed cosmic history. The bursts became flashlights illuminating structures too faint to see otherwise. Milliseconds helping map billions of light years. The disproportion still feels almost funny somehow. And through all of this, the mystery itself never fully disappeared. That may be the most fascinating part. Astronomers understand far more about FRBs now than during the first discoveries at Parkes Observatory years ago. Thousands of bursts have been detected, repeaters identified, magnetars connected observationally to FRB-like events, and still major questions remain open. Do all FRBs come from magnetars? Why do some repeat while others remain silent forever? What creates the complicated structures hidden inside certain bursts? Why do some appear in unexpected galactic environments? Could multiple mechanisms exist simultaneously? The universe continues withholding complete answers, not maliciously, just naturally. Reality is under no obligation to become simple, because humans prefer neat explanations. There is another quiet lesson hidden inside FRBs too. Human beings often imagine science as a process moving steadily towards certainty, but astronomy rarely feels like that internally. It feels more like standing inside a dark room while someone keeps briefly flicking lights on and off. A tiny glimpse here, another clue there, patterns emerging gradually. FRBs embody that feeling perfectly. Milliseconds of information arriving from billions of light years away, enough to reveal astonishing truths. Not enough to solve everything completely, at least not yet. And maybe that incompleteness is part of what makes astronomy soothing sometimes. The universe remains larger than human understanding, not because humanity is failing, but because reality itself is staggeringly detailed. There will always be more to learn, more signals crossing space, more mysteries waiting quietly inside telescope data, more nights beneath the stars. Late at night, that realization can feel strangely peaceful. Human problems often shrink slightly against cosmic scales. Emails lose urgency. Awkward conversations fade a little. Daily anxieties become less permanent when viewed beside galaxies and neutron stars and signals travelling longer than civilization survive. The universe does not erase human life. It simply places it into perspective, and perspective can be calming, especially tonight, especially now. Because somewhere beyond the visible stars overhead, another FRB is probably crossing darkness already. The signal itself does not know Earth exists. It does not know humanity built radio telescopes. It does not know scientists wait beneath quiet skies listening carefully for brief disturbances hidden inside cosmic noise. The burst simply travels according to the laws of physics, patiently, steadily, across expanding space-time. Perhaps tonight, somewhere in Australia or Canada or China or the deserts of New Mexico, a radio telescope will detect it. Computers will react instantly. Data streams will spike. Astronomers may wake suddenly from sleep to check incoming observations, and for a few milliseconds humanity will overhear another whisper from deep space, another ancient traveller arriving after billions of years alone in the dark. Then silence again, at least until the next burst arrives, which it almost certainly will. Because the universe keeps speaking, quietly, briefly, mysteriously. And now, for the first time in cosmic history, there is finally a species listening closely enough to hear it.